Right now, as you hear these words, a machine floating 1 million miles from Earth is staring at something that should not exist. Neptune, the ice giant at the edge of our solar system, has been hiding a secret for 4 billion years. And James Webb Space Telescope just tore away the veil. For decades, we thought we understood this frozen world. A pale blue sphere wrapped in methane clouds, spinning quietly in the cosmic deep. Temperatures hovering at -370 degrees Fahrenheit. Winds screaming at 1,500 miles per hour through an atmosphere we assumed was dead and predictable. Textbooks called it stable. Scientists called it solved. They were catastrophically wrong. Webb pointed its 18 gold-plated mirrors at Neptune in July 2022. The data that came back made astrophysicists question whether they had been studying the same planet for the past 2 centuries. Atmospheric signatures that violate thermodynamic models. Chemical processes operating under conditions that physics says should be impossible. Energy emissions from regions that should be frozen into absolute silence. This is not about discovering another moon or finding water ice in unexpected locations. This is about Neptune behaving like a world that is fundamentally different from everything we thought we knew. The planet is not following the rules, and when an object 8 times more massive than Earth stops obeying the laws of physics, you do not get to call it an anomaly. You have to accept that your understanding of reality is incomplete. The discovery touches something deeper than planetary science. It reaches into the foundations of how we model atmospheres, how we understand ice giant formation, and how we predict the behavior of worlds beyond our solar system. If Neptune can surprise us this profoundly after centuries of observation, what does that say about the thousands of exoplanets we claim to understand based on a few pixels of light? The mechanism Webb detected operates in Neptune's stratosphere, a region we thought was thermally uniform. A zone that should be as quiet as a tomb. Instead, Webb found it glowing with unexpected warmth. The temperature readings make no sense. The chemical signatures suggest processes that should not be occurring at those altitudes. And the implications force us to rewrite atmospheric physics for every ice giant in the universe. Scientists are using words they rarely deploy: unprecedented, inexplicable, paradigm-breaking. These are not the terms you use when your instruments need calibration. These are the words you speak when the universe reveals that you have been fundamentally misunderstanding something for your entire career. Neptune sits 30 times farther from the Sun than Earth. At that distance, solar energy is 900 times weaker than what we receive. The planet should be frozen into near-uniform cold. Its stratosphere should be a layer of methane ice hovering at temperatures barely above absolute zero. That is what every atmospheric model predicted. That is what Voyager 2 seemed to confirm in 1989. Webb discovered that Neptune's stratosphere is hot. Not slightly warm, hot. In some regions, temperatures reach -100 degrees Fahrenheit. That sounds cold to human ears. But in a place where temperatures should be -370 degrees, finding regions 170 degrees warmer is like discovering a blast furnace operating in Antarctica. The warmth is not uniform. It concentrates around Neptune's south pole in patterns that suggest active heating mechanisms operating right now. Solar radiation cannot explain it. The sun is too weak at that distance. Internal heat cannot explain it. Neptune's core is too deep and too insulated by thousands of miles of ice and compressed gases. Something is heating Neptune's stratosphere. Something powerful, something we did not predict and cannot immediately explain. And Webb has given us the clearest view of this impossible phenomenon that humanity has ever achieved. This discovery is the entry point into a larger mystery, a doorway that opens onto questions about planetary formation, atmospheric chemistry, and the fundamental nature of ice giants throughout the galaxy. As we follow this investigation deeper, you will encounter phenomena that challenge your assumptions about how planets work and why they behave the way they do. Prepare yourselves, we begin. "18 months before James Webb pointed its sensors at Neptune, ground-based telescopes in Chile and Hawaii were watching the ice giant do something impossible. Between 2018 and 2020, Neptune's south pole warmed by 11 degrees Celsius in just 2 years. Not 11 degrees across millennia of geological time, 11 degrees in 730 days. Michael Roman at the University of Leicester first noticed the anomaly while analyzing thermal infrared data from the Very Large Telescope. He was tracking Neptune's stratosphere, the atmospheric layer sitting directly above the planet's weather zone. This is the region where temperatures should behave predictably, where physics operates according to models refined over decades of planetary science, where nothing should surprise us anymore. The data showed a bright thermal hotspot blazing at Neptune's south pole, a region glowing in infrared wavelengths with intensity that violated every atmospheric model. Roman ran the numbers again, checked the calibrations, compared datasets from multiple telescopes spanning different observation periods. The conclusion remained inescapable. Something was heating Neptune's polar stratosphere at rates that should not be possible. The temperature spike defies straightforward explanation. Neptune orbits 30 times farther from the Sun than Earth. At that distance, solar energy arrives diminished by a factor of 900. The Sun appears in Neptune's sky as little more than an exceptionally bright star. Its radiation cannot meaningfully warm the planet's upper atmosphere. Yet, here was direct observational evidence of rapid atmospheric heating occurring in real time. The warming appeared even more bizarre when placed in context. For the previous 15 years, from 2003 through 2018, Neptune's globally averaged stratospheric temperature had been dropping. Thermal infrared observations from the European Southern Observatory's Very Large Telescope, the Subaru telescope atop Mauna Kea, and NASA's now-retired Spitzer Space Telescope all confirm the same trend. Neptune was cooling, its stratosphere losing roughly 8 degrees Celsius over that period. This cooling made no sense either. Neptune entered its southern summer around 2005. Summer on Neptune lasts over 40 Earth years due to the planet's 165-year orbital period. As summer progressed, atmospheric temperatures should have gradually increased. Solar radiation, however feeble at that distance, should warm the summer hemisphere through consistent exposure over decades. Instead, the planet cooled, then abruptly reversed course with dramatic polar warming. Lee Fletcher, professor of planetary science at the University of Leicester, described the observations as pointing toward a far more complicated picture of Neptune's atmosphere than anyone anticipated. The temperature variations challenge fundamental assumptions about ice giant atmospheric dynamics. They suggest processes operating in Neptune's stratosphere that current physics cannot adequately explain. When James Webb Space Telescope turned its instruments toward Neptune in September 2022, it brought capabilities specifically designed to resolve these mysteries. Webb's near-infrared camera captured Neptune in wavelengths between 0.6 and 5 microns. At these infrared frequencies, methane gas in Neptune's atmosphere absorbs nearly all incoming light. The planet appears dark except where high-altitude clouds reflect sunlight before methane absorption occurs. But Webb's observations revealed more than cloud structures. The telescope's mid-infrared instrument, known as MIRI, provided unprecedented mapping of Neptune's stratospheric chemistry and temperature distribution. MIRI operates at wavelengths between 5 and 28 microns, perfectly suited for detecting thermal emissions from planetary atmospheres. At these wavelengths, atmospheric gases emit infrared radiation based on their temperature. Warmer regions glow brighter. Cooler regions appear dimmer. The data Webb collected confirmed the ground-based observations and revealed additional complexity. The south polar warming was not uniform. It concentrated in specific longitudinal bands. It showed vertical structures suggesting different heating mechanisms operating at different altitudes. The temperature distribution implied active atmospheric circulation transporting energy from elsewhere in the planet's atmosphere or interior. Webb also measured Neptune's upper atmosphere temperature for the first time since Voyager 2's flyby in 1989. The results shocked researchers. Neptune's upper atmosphere had cooled by several hundred degrees Celsius since Voyager's measurements. Henrik Melin from Northumbria University, who helped analyze the Webb data, stated he was astonished by the magnitude of cooling. The upper atmosphere temperature drop suggested that Neptune's entire atmospheric thermal structure was undergoing dramatic changes. The cooling of the upper atmosphere while the stratosphere experiences localized warming creates a thermal paradox. Energy must be flowing somewhere. Heat cannot simply vanish. If the upper atmosphere is cooling, that energy is either radiating into space at enhanced rates or being transported downward into deeper atmospheric layers. Either explanation requires mechanisms that current models do not adequately describe. The stratospheric temperature variations correlate with changes in Neptune's cloud activity. Ground-based telescopes observing invisible wavelengths noted that bright cloud features in Neptune's atmosphere varied in frequency and intensity over the same time periods when stratospheric temperatures fluctuated. More clouds appeared during years when the stratosphere was warmer. Fewer clouds formed during cooler periods. This correlation suggests a connection between stratospheric heating and atmospheric dynamics in the troposphere below. Cloud formation on Neptune occurs when methane gas condenses at specific temperature and pressure thresholds. If stratospheric heating somehow influences tropospheric temperatures, it could trigger or suppress cloud formation through mechanisms that bypass normal meteorological processes. One hypothesis proposes that Neptune's stratospheric chemistry might be changing in ways that alter how effectively the atmosphere radiates heat. Methane in the stratosphere can be broken apart by ultraviolet radiation from the sun. This photochemical process creates ethane, acetylene, and other hydrocarbon compounds. These molecules have different radiative properties than methane. They absorb and emit infrared radiation at different wavelengths and with different efficiencies. If the abundance of these photochemical products varies over time, the stratosphere's ability to cool itself through infrared radiation would change accordingly. More ethane and acetylene means more efficient cooling. Less of these compounds means less cooling and thus warmer temperatures. But this explanation requires explaining why photochemical production rates would vary so dramatically on timescales of just years to decades. Another possibility involves Neptune's 11-year solar activity cycle connection. The sun's output of ultraviolet radiation varies with its 11-year sunspot cycle. During solar maximum, when sunspot numbers peak, the sun emits more UV radiation. During solar minimum, UV output decreases. Some evidence suggests Neptune's brightness in visible wavelengths correlates with solar activity levels. If solar UV variations affect Neptune's stratospheric chemistry, they could drive the temperature changes through altered photochemical production of radiatively active molecules. The timing roughly matches. The stratospheric cooling from 2003 to 2018 corresponds to 1.5 solar cycles. The rapid polar warming from 2018 to 2020 occurred during rising solar activity, leading to the solar cycle 25 maximum. But solar cycle forcing faces significant problems. The magnitude of UV variation between solar minimum and maximum is relatively small. The resulting changes in stratospheric chemistry should produce temperature variations of just a few degrees at most. The observed temperature swings of 8 degrees globally and 11 degrees at the pole exceed what solar forcing alone can explain. Internal heating from Neptune's core presents another potential mechanism. Neptune radiates 2.6 times more energy than it receives from the sun. This excess heat comes from the planet's interior. Primordial heat left over from Neptune's formation billions of years ago still slowly leaks outward. Additionally, ongoing differentiation processes, where heavier materials sink toward the core while lighter materials rise, generate heat through gravitational potential energy conversion. If the rate of internal heat transport to the surface varies over time, it could drive atmospheric temperature changes. Enhanced upward heat flow would warm the atmosphere from below. Reduced heat flow would allow cooling. But explaining rapid changes in internal heat transport poses challenges. Neptune's interior is thought to be relatively stable on timescales relevant to these observations. Significant variations in heat transport would require convective processes deep within the planet to change dramatically over just years or decades. The south polar warming specifically suggests localized heating mechanisms. On Earth, polar warming often results from atmospheric circulation patterns that transport heat from lower latitudes toward the poles. The Ferrel cell circulation in Earth's mid-latitudes, combined with poleward atmospheric flows, can concentrate warmth at high latitudes during certain climate patterns. Neptune might experience analogous circulation. The planet's rapid rotation, completing one day in just 16 hours, drives powerful Coriolis forces that organize atmospheric flow into latitudinal bands. Meridional circulation, the north-south atmospheric transport, could potentially concentrate heat at the poles under specific conditions. If this circulation intensified between 2018 and 2020, it could explain the polar warming through heat transport from lower latitudes. Webb's high-resolution atmospheric mapping will test this hypothesis. If circulation changes drove the warming, Webb should detect temperature gradients and wind patterns consistent with enhanced heat transport toward the South Pole. The telescope's ability to map atmospheric composition at different altitudes will reveal whether specific gases are being transported poleward in patterns that match theoretical circulation models. The mystery deepens when considering Neptune's magnetic field geometry. Neptune's magnetic field tilts 47 degrees relative to its rotation axis. Additionally, the field is offset from the planet's center by 0.55 Neptune radii. This bizarre geometry creates a magnetic environment unlike any other planet in the solar system. The magnetic poles are not near the rotation poles. Magnetic field lines connect to the atmosphere at mid-latitudes rather than polar regions. This magnetic geometry affects where auroras form. On Earth, Jupiter, Saturn, and Uranus, auroras occur near the poles where magnetic field lines funnel charged particles into the upper atmosphere. On Neptune, auroras should appear at much lower latitudes where the tilted, offset magnetic field intersects the atmosphere. Webb's detection of auroral emissions confirmed this. Bright spots of aurora appeared scattered across Neptune's disk rather than concentrated at the poles. Auroras deposit energy into the atmosphere. Charged particles from the solar wind, trapped by Neptune's magnetic field, spiral along field lines until they collide with atmospheric gases. These collisions heat the upper atmosphere and ionize atoms and molecules, creating the glowing aurorae. On Earth, auroral heating can raise upper atmospheric temperatures by hundreds of degrees in localized regions. If auroral intensity on Neptune varies significantly over time, it could drive upper atmospheric temperature changes. Enhanced auroral activity would heat the upper atmosphere. Reduced activity would allow cooling, but connecting auroral heating to stratospheric temperature changes requires energy transport mechanisms linking these atmospheric layers. Webb detected high concentrations of the H3+ ion in Neptune's upper atmosphere. This molecular ion forms when hydrogen molecules are ionized and then react with additional hydrogen molecules. H3+ is a clear marker of auroral activity because the ionization requires high-energy processes like those occurring during auroral particle bombardment. The presence of H3+ confirms that Neptune's upper atmosphere is actively being heated by auroral processes. But the H3+ detection also confirmed that the upper atmosphere had cooled dramatically since Voyager 2's measurements. This creates an apparent contradiction. Auroral activity is occurring, depositing energy into the upper atmosphere. Yet the upper atmosphere is significantly cooler than it was 33 years ago. Either auroral activity has decreased substantially since Voyager's flyby, or other cooling processes are overwhelming the auroral heating. The stratospheric hotspot at Neptune's south pole sits well below the altitudes where aurora occurs. Stratospheric heating must have a different source than auroral processes. Yet the timing of stratospheric warming coinciding with changes in upper atmospheric temperature suggests some connection between atmospheric layers. Energy is being redistributed vertically through Neptune's atmosphere in ways that current models cannot adequately explain. Webb's observations also revealed subtle variations in Neptune's ring system brightness that correlate with atmospheric temperature changes. The rings appear slightly brighter during periods when the stratosphere is warmer. This unexpected correlation hints at connections between Neptune's atmosphere and its ring system that no one anticipated. One possibility involves charged particles. Neptune's magnetic field extends beyond the planet's surface to influence the space environment around it. Charged particles trapped in this magnetosphere can interact with ring particles, altering their surface properties and reflectivity. If atmospheric heating somehow affects magnetospheric particle populations, it could indirectly influence ring brightness through complex chains of interactions. The stratospheric heat mystery represents more than an isolated puzzle about one planet's atmospheric behavior. Neptune serves as the archetype for ice giants throughout the galaxy. Thousands of exoplanets discovered by transit surveys fall into the sub-Neptune or Neptune mass category. These worlds, too distant and faint for detailed atmospheric characterization, remain largely mysterious. Understanding Neptune's atmospheric processes provides the only template for interpreting observations of these countless distant analogs. If Neptune's atmosphere can change this dramatically on decadal timescales through mechanisms we don't understand, what does that imply about atmospheric models being applied to exoplanets? We observe these distant worlds during brief snapshot moments of their potentially billions-year evolutionary histories. We assume their atmospheres are in stable states that our models can reliably characterize. Neptune demonstrates that ice giant atmospheres can undergo rapid, dramatic changes driven by processes that remain unclear even for the one example we can study in detail. The stratospheric heating also raises questions about planetary heat budgets. Neptune radiates more energy than it receives from the Sun. This excess heat must come from the planet's interior. But how interior heat reaches the surface and how it gets distributed through the atmosphere involves complex convection, conduction, and radiative processes that remain poorly understood. The observed temperature variations suggest that these processes are far more dynamic and variable than simple steady-state models assume. As Webb continues observing Neptune through different seasons and solar cycle phases, it will build a long-term dataset tracking how the stratospheric temperatures evolve. This temporal coverage will help discriminate between competing hypotheses. If temperatures track solar activity levels, it supports external forcing mechanisms. If temperatures vary independently of solar cycles, it points toward internal or atmospheric processes as the primary drivers. The mystery refuses simple answers. Neptune is not supposed to surprise us. It should be a frozen, relatively inert world slowly orbiting in the outer darkness. Instead, it presents as a dynamically active planet with atmospheric processes operating through mechanisms that challenge our fundamental understanding of how ice giant atmospheres work. Methane turned Neptune into a ghost. When James Webb observed the ice giant through its near-infrared camera in September 2022, the planet appeared almost invisible against the backdrop of space. Where Hubble's visible light images showed Neptune glowing pale blue, Webb's infrared vision revealed a dark sphere barely distinguishable from the cosmic void surrounding it. This disappearing act results from methane's extraordinary ability to absorb infrared radiation. Methane gas, which comprises approximately 2 to 3% of Neptune's atmosphere, acts as a near-perfect infrared absorber. At wavelengths between 0.6 and 5 microns, where Webb's NIR cam operates, methane molecules intercept nearly all incoming light. Photons that penetrate Neptune's upper atmosphere encounter methane gas that swallows them completely. The energy gets absorbed. The light vanishes. The planet goes dark. Only high-altitude clouds escape this infrared blackout. Methane ice clouds forming in Neptune's upper troposphere and lower stratosphere reflect sunlight before it can reach the methane-rich layers below. These clouds appear as brilliant white streaks and spots against Neptune's dark disk. They glow bright in Webb's images, not because they emit light, but because they sit high enough to reflect sunlight before methane absorption erases it. The methane absorption creates a natural filter that allows Webb to map Neptune's three-dimensional cloud structure with unprecedented precision. Bright clouds mark regions where atmospheric dynamics have lifted material above the main methane layer. Darker regions indicate areas where clouds sit deeper in the atmosphere, where methane has already absorbed the incoming light. The resulting image provides a vertical map of Neptune's atmosphere, showing which regions have active convection lifting material to high altitudes. But Webb's observations revealed atmospheric behavior that challenges fundamental assumptions about methane chemistry on ice giants. The telescope detected methane abundance variations that should not exist according to photochemical models developed over decades of planetary science research. Methane photochemistry on Neptune operates through well-understood processes. Solar ultraviolet radiation with wavelengths shorter than 145 nanometers penetrates Neptune's stratosphere. When these energetic photons strike methane molecules, they break chemical bonds through photolysis. The methane molecule, CH4, splits apart, creating free radicals and initiating a cascade of chemical reactions. The photolysis products include methyl radicals, acetylene, ethylene, ethane, methylacetylene, and diacetylene. These hydrocarbons form through complex reaction networks where methane fragments recombine in various configurations. Some reactions require multiple steps. Others proceed rapidly through chain mechanisms where one photolysis event triggers numerous subsequent reactions. This photochemical processing should establish predictable methane abundance profiles in Neptune's stratosphere. Methane concentrations should decrease with altitude, as photolysis destroys molecules faster than atmospheric mixing can replenish them. The depletion rate depends on UV flux, atmospheric mixing strength, and reaction kinetics. Models incorporating these factors predict specific methane profiles that can be compared against observations. Webb's spectroscopic measurements revealed methane distributions that violate these predictions. In some atmospheric regions, methane appears more abundant than photochemical destruction rates allow. In others, methane is depleted beyond what photolysis alone can explain. The discrepancies suggest that Neptune's atmosphere contains methane sources or sinks that current models do not include. One anomaly appears in Neptune's equatorial region. Webb detected an enhanced methane signature encircling the planet's equator, appearing as a thin bright line in infrared wavelengths. This equatorial brightness suggests higher temperatures or altered methane abundances, specifically at low latitudes. The feature corresponds to a region where Neptune's atmospheric circulation patterns should create descent and warming. On Earth, descending air masses at roughly 30 degrees latitude create the subtropical deserts. As air descends, adiabatic compression heats it. This warming increases the atmosphere's capacity to hold moisture, creating clear, dry conditions. Neptune likely experiences analogous circulation with rising air at the equator and descending air at mid-latitudes, driven by the planet's rapid rotation and internal heat source. But the methane enhancement at Neptune's equator cannot result simply from temperature increases. Even if descending air warms the equatorial atmosphere, it should not increase methane abundance. Methane comes from deeper atmospheric layers where it exists in higher concentrations. For the equator to show enhanced methane, circulation must be transporting methane-rich air upward from below, faster than photolysis can destroy it. This implies vigorous vertical mixing at Neptune's equator. Atmospheric convection must be carrying methane from the troposphere into the stratosphere, at rates exceeding what standard atmospheric models predict. The mixing rates required to maintain observed methane abundances suggest eddy diffusion coefficients of 10 to the power 11 to 10 to the power 12 square centimeters per second. These values exceed measurements from other atmospheric regions by factors of 10 to 100. Why Neptune's equator experiences such vigorous mixing remains unclear. One possibility involves the interaction between the planet's rapid rotation and its internal heat source. Neptune rotates once every 16.1 hours, creating strong Coriolis forces. These forces, combined with heat rising from the interior, drive atmospheric circulation patterns. At the equator, where Coriolis effects are weakest, convection might penetrate higher into the stratosphere than at other latitudes. Another methane anomaly appears in Neptune's polar regions. Webb observations revealed methane absorption features at high latitudes that suggest cooler temperatures than expected. Colder atmospheric temperatures allow methane to condense more readily. If Neptune's poles are colder than models predict, methane ice clouds should form at lower altitudes, affecting the planet's radiative balance and atmospheric dynamics. The polar methane depletion might connect to the stratospheric warming observed at Neptune's south pole. If circulation patterns are transporting methane away from the poles toward lower latitudes, it would deplete polar methane while enhancing equatorial abundances. This meridional transport would require sustained atmospheric flows connecting the poles to the equator through mechanisms not included in current circulation models. Webb also detected temporal variations in Neptune's methane distribution. Observations separated by weeks showed changes in cloud brightness and distribution patterns that indicate dynamic atmospheric processes operating on relatively short timescales. These variations suggest that Neptune's atmosphere responds to forcing mechanisms that vary over days to weeks, rather than remaining in steady-state equilibrium. The photochemical products of methane destruction present their own mysteries. When UV radiation breaks apart methane, the resulting hydrocarbons should accumulate in Neptune's stratosphere. Ethane and acetylene, the primary photolysis products, have been detected spectroscopically at abundances roughly consistent with photochemical predictions. But other expected products appear either more or less abundant than models anticipate. Diacetylene, formed through acetylene photolysis, should exist at measurable levels in Neptune's upper stratosphere. Yet observations consistently find lower diacetylene abundances than predictions suggest. Either the formation rate is slower than models calculate, or destruction mechanisms are removing diacetylene faster than expected. One possibility involves condensation. If diacetylene forms ice particles that settle downward, it would remove the molecule from the gas phase before it can accumulate to predicted levels. The hydrocarbon haze layer in Neptune's stratosphere provides evidence for this condensation process. Observations at visible and near-infrared wavelengths detect aerosol particles distributed throughout the lower stratosphere. These particles appear to be composed primarily of ethane ice, acetylene ice, and polymerized hydrocarbons. The haze forms when photochemical products reach concentrations high enough to condense at stratospheric temperatures and pressures. But the haze distribution shows unexpected patterns. Some regions of Neptune's stratosphere contain much thicker haze layers than others. The haze appears concentrated at specific latitudes and altitudes, suggesting that atmospheric dynamics control where hydrocarbon ices can accumulate. Regions with strong vertical mixing keep hydrocarbons suspended as gases, preventing condensation. Calmer regions allow condensation to proceed, forming visible haze layers. Webb's observations revealed fine structure in the haze distribution that had never been seen before. The telescope's spatial resolution allowed mapping of haze variations on scales of hundreds of kilometers. This detailed mapping showed that the haze forms discrete layers at specific altitudes rather than being uniformly distributed. The layering suggests that temperature inversions or chemical gradients create stable atmospheric zones where condensation preferentially occurs. The methane paradox deepens when considering Neptune's interior processes. The planet radiates 2.6 times more energy than it receives from the Sun. This excess heat comes from internal sources, primarily gravitational differentiation, where heavier materials sink toward the core, releasing potential energy as heat. This internal heating drives convection in Neptune's interior, transporting heat outward toward the surface. If convection extends into the lower atmosphere, it could transport methane from deep interior layers, where methane is abundant, upward into regions where photolysis can destroy it. The rate of this vertical transport determines how much methane reaches the stratosphere and how quickly photolysis can deplete it. Current models assume relatively modest vertical mixing rates, but Webb's observations suggest mixing might be far more vigorous than these models allow. Some theoretical studies propose that Neptune might experience episodic convective events, where large-scale overturning suddenly transports deep atmospheric material to high altitudes. These convective storms would temporarily flood the stratosphere with methane from below, overwhelming photochemical destruction, and creating the methane abundance anomalies Webb detected. After the storm subsides, photolysis would gradually deplete the excess methane until the next convective event occurs. This episodic convection model predicts temporal variability in stratospheric methane abundances. Observations made at different times should show varying methane signatures depending on how recently a convective event occurred. Webb's detection of temporal changes in Neptune's cloud structures and methane distributions provides circumstantial support for this idea, though definitive confirmation would require continuous monitoring over extended periods. The methane mystery extends beyond Neptune to become a fundamental problem for understanding ice giants throughout the galaxy. Astronomers have discovered thousands of exoplanets falling into the Neptune mass category. These sub-Neptunes and super-Earths orbit other stars at various distances, experiencing different radiation environments. Many exist in their host stars, habitable zones where liquid water could theoretically exist on planetary surfaces. Webb has begun characterizing the atmospheres of some Neptune-mass exoplanets through transit spectroscopy. As these planets pass in front of their host stars, starlight filters through their atmospheres. Different molecules absorb light at characteristic wavelengths, creating spectral fingerprints that reveal atmospheric composition. These observations have produced surprising results that echo Neptune's methane mysteries. Several exoplanets that should contain abundant methane show severe methane depletion. The exoplanet WASP-107b, a warm Neptune orbiting a Sun-like star, contains methane at abundances 3 orders of magnitude below equilibrium expectations. Webb's detection of methane in WASP-107b represented a breakthrough because previous observations failed to find the molecule despite its expected abundance. The methane depletion in WASP-107b results from similar processes affecting Neptune. Vertical mixing transports methane from the planet's hot interior upward into cooler atmospheric layers. Photochemistry destroys some methane, but the primary depletion mechanism appears to be chemical reactions favoring carbon monoxide over methane when interior temperatures exceed certain thresholds. At temperatures above roughly 800 Kelvin, thermodynamic equilibrium favors carbon monoxide and carbon dioxide over methane. If WASP-107b's interior is hot enough, deep atmospheric layers will contain mostly carbon monoxide. When vertical mixing transports this gas upward, the upper atmosphere ends up methane depleted regardless of photochemical processes. Webb's observations confirm that WASP-107b has an interior temperature of 460 Kelvin, far hotter than previous models predicted. This realization fundamentally changes our understanding of Neptune-class planets. The connection between interior heat and atmospheric chemistry means that observing atmospheric methane abundances provides direct information about interior temperatures and mixing rates. This linkage makes methane a powerful diagnostic tool for probing planetary interiors that are otherwise inaccessible to observation. Neptune's own interior temperature remains uncertain. The planet's energy balance indicates internal heat production, but determining the exact interior temperature structure requires modeling that depends on uncertain parameters like internal composition and heat transport mechanisms. If Neptune's deep atmosphere is hotter than standard models assume, it would affect how much methane can exist there and how vigorously mixing must operate to maintain observed stratospheric abundances. Webb's methane observations also revealed unexpected connections to Neptune's cloud formation processes. Methane ice clouds should form where temperatures drop below methane's condensation point, typically around 60 Kelvin at relevant atmospheric pressures. But Webb detected bright methane ice clouds at altitudes where temperatures appear too warm for methane condensation to occur, according to standard phase diagrams. This suggests either that atmospheric temperatures at cloud-forming altitudes are colder than models predict, or that the clouds are forming through non-standard processes. One possibility involves adiabatic cooling. If atmospheric convection creates strong updrafts, rising air expands and cools adiabatically. This cooling might drop temperatures below the condensation point in localized regions, allowing methane ice to form, even though the surrounding atmosphere remains warm. Another possibility involves heterogeneous nucleation. Ice crystals might be forming on pre-existing aerosol particles that serve as condensation nuclei. These particles could include photochemically produced hydrocarbons, externally supplied dust from meteoric ablation, or material transported upward from deeper atmospheric layers. If nucleation occurs preferentially on these particles, methane ice could form at temperatures slightly warmer than required for homogeneous condensation. The distribution of methane ice clouds across Neptune's disk provides clues about atmospheric circulation patterns. Webb images show that bright clouds cluster at specific latitudes, particularly in the mid-latitudes between 30 and 60 degrees in both hemispheres. This latitudinal banding suggests that atmospheric dynamics preferentially create conditions favorable for cloud formation at these specific zones. On Jupiter and Saturn, latitudinal banding results from alternating eastward and westward jet streams. Rising air at certain latitudes creates cloud formations, while descending air at other latitudes suppresses clouds. Neptune likely experiences similar jet stream patterns, though less is known about Neptune's winds compared to the gas giants. Webb's cloud observations provide new constraints on where vertical motion occurs in Neptune's atmosphere, helping to map its circulation patterns. The temporal evolution of Neptune's clouds adds another layer of complexity. Ground-based telescopes observing Neptune over decades have documented that bright cloud features appear and disappear on timescales of days to weeks. Some clouds persist for months, while others vanish within hours. This variability indicates that Neptune's atmosphere responds dynamically to forcing that varies rapidly. Webb's ability to observe Neptune repeatedly with identical instrumentation and wavelength coverage will allow systematic tracking of how cloud features evolve. Time series observations can reveal whether clouds form preferentially at certain times in Neptune's year, which lasts 165 Earth years. They can also test whether solar cycle variations affect cloud formation rates by altering UV flux reaching Neptune's stratosphere. The methane paradox ultimately reveals how little we understand about ice giant atmospheres despite decades of study. Neptune should be relatively simple compared to Jupiter or Saturn. Its atmosphere contains fewer complex hydrocarbons. Its cloud structures are less diverse. Its weather patterns should be more straightforward to model. Yet Neptune continues producing observations that defy explanation. This difficulty understanding Neptune raises disturbing questions about our ability to interpret observations of exoplanets. If we cannot adequately explain methane behavior on Neptune, which we can observe directly across multiple wavelengths with our most powerful telescopes, how can we confidently interpret the atmospheric spectra of distant worlds observed through brief transits? The methane mystery suggests that ice giant atmospheres operate through processes that remain hidden from our current observational and theoretical approaches. Vertical mixing rates, interior temperature structures, convective dynamics, and cloud formation mechanisms all appear more complex than simple steady-state models assume. Neptune's atmosphere is not a passive envelope slowly responding to external forcing. It is a dynamic system where interior processes, photochemistry, circulation patterns, and condensation physics interact in ways we are only beginning to understand. For 33 years, Neptune's rings existed primarily as data in scientific archives. Voyager 2 captured them during its flyby in August 1989. Brief glimpses, faint tracings against the black void. Then, silence. Ground-based telescopes lacked the resolution to see them. Hubble could barely detect the brightest components. The rings became astronomical ghosts, known to exist but invisible to observation. James Webb changed that in a single exposure. On July 12, 2022, Webb's near-infrared camera captured Neptune for 85 seconds. When the image processed, planetary scientist Heidi Hammel saw what no human had witnessed in over 3 decades. Neptune's complete ring system blazing across her screen in unprecedented clarity. She admitted to ugly crying, yelling at her family to look, making even her cats witness what Webb had revealed. The rings appeared sharper than Voyager's images, despite Webb observing from 1 million miles away while Voyager flew directly past the planet. Webb's 18 hexagonal mirror segments, aligned to nanometer precision, delivered image stability that Voyager's cameras could never achieve. The telescope's infrared sensitivity allowed it to see through the glare that normally overwhelms faint structures close to bright planetary disks. Neptune possesses 5 named rings. The Gale ring sits closest to the planet at 42,000 kilometers from Neptune's center. Then comes the Leverrier ring at 53,000 kilometers. The Lassell ring forms a broad diffuse band between 53,000 and 57,000 kilometers. The Arago ring marks the outer boundary of the Lassell system at 57,000 kilometers. Finally, the Adams ring orbits at 63,000 kilometers, 5.5 Neptune radii from the planet's center. But calling them rings oversimplifies their nature. These structures are not solid bands like Saturn's spectacular rings. They are tenuous collections of dust and ice particles, so sparse that you could fly a spacecraft through them without hitting anything. Their optical depth, the fraction of light they block, ranges from 0.001 to 0.1. This means 99 to 99.9% of light passes straight through unaffected. The Gala ring is Neptune's faintest structure, nearly invisible even to Webb. It consists of fine dust particles, perhaps micrometers in diameter. These particles scatter light weakly, creating a barely detectable glow against the darkness. The ring's existence was inferred from Voyager data but remained unconfirmed by subsequent observations until Webb finally captured it. The Leverrier ring appears as a crisp, bright line in Webb's images. This narrow ring, just 100 kilometers wide, contains particles large enough to efficiently scatter infrared light. The ring's sharpness indicates that gravitational shepherding by unseen moonlets confines the particles to a narrow band. Without such confinement, particle collisions and orbital dynamics would spread the ring into a diffuse sheet. The Lassell ring forms a broad, dusty region surrounding the Leverrier ring. This extended structure likely represents the debris field from collisions between larger parent bodies. When moonlets crash together at orbital velocities, they shatter into clouds of dust that spread along their orbital paths. The Lassell ring might be the collective debris from hundreds or thousands of such collisions occurring over millions of years. The Adams ring dominates Webb's images as the brightest component of Neptune's ring system, but calling it a ring misleads. The Adams structure contains 5 distinct arcs, rather than forming a continuous circle. These arcs, named Fraternité, Égalité 1, Égalité 2, Liberté, and Courage, using French Revolutionary terminology, occupy specific positions along the orbit at 63,000 kilometers. The arcs should not exist. Orbital mechanics dictates that material in an arc should spread into a complete ring within years. Differential rotation means inner particles orbit faster than outer particles. This velocity shear stretches any clump into a filament. Collisions between particles further homogenize the distribution. Within a few orbital periods, any initial clustering should disappear, leaving a uniform ring. Yet the Adams arcs persist. Voyager 2 photographed them in 1989. Ground-based stellar occultations detected them in the 1980s and 90s. Hubble imaged them in the 2000s. Webb captured them in 2022. The arcs occupy nearly identical orbital positions across 4 decades of observations. Something stabilizes them against the forces that should destroy them. The leading explanation invokes orbital resonances with Neptune's moon Galatea. This small satellite, just 176 kilometers in diameter, orbits just inside the Adams ring at 62,000 kilometers. Galatea's gravitational influence creates resonant locations where particles experience periodic perturbations that concentrate them into stable configurations. The specific resonance appears to be 42 to 43 mean motion resonance. For every 43 orbits Galatea completes, particles in the arcs complete exactly 42 orbits. This creates a gravitational lockstep where Galatea's gravity reinforces itself at specific locations, preventing particles from spreading. The mathematics of orbital resonance predicts 5 stable points at this particular resonance ratio, matching the 5 observed arcs. But the resonance explanation faces difficulties. The predicted arc widths based on Galatea's mass are narrower than observed. The arcs should contain sharp boundaries where resonance forces are strongest. Instead, they show gradual transitions from dense cores to diffuse edges. The optical depth profiles do not match theoretical predictions, suggesting that additional physics beyond simple resonance mechanics must be operating. Webb's observations revealed new details about the arcs' internal structure. Previous images showed the arcs as uniform bright segments. Webb resolved clumpiness within the arcs with brightness variations on scales of hundreds of kilometers. These substructures indicate that the arcs contain discrete concentrations of material rather than smooth distributions. The clumps might be debris from relatively recent collisions. When larger parent bodies collide, they produce swarms of fragments that initially stay grouped together. Over time, orbital dynamics disperse these swarms, but for periods of years to decades after collision, the debris remains clumped. Webb might be seeing multiple collision remnants within each arc, representing a history of impacts among the moonlet population. The arcs also showed temporal changes between Voyager observations and Webb's images. The Liberté arc has faded dramatically. In Voyager images from 1989, Liberté appeared comparable in brightness to the other arcs. Ground-based observations through the 1990s and 2000s showed steady dimming. By the time Webb observed Neptune, Liberté had nearly disappeared. Its optical depth dropped from 0.09 in 1989 to below 0.02 in 2022. The Courage arc demonstrates opposite behavior. Voyager barely detected it in 1989. Ground-based observations in 1998 showed Courage had suddenly brightened. By 2022, when Webb observed it, Courage had returned to faintness. This flare and fade cycle suggests episodic events, perhaps major collisions, produce temporary brightness enhancements that decay over years. The arc positions also shifted. Between 1989 and 2022, the Courage arc jumped forward by 8 degrees in orbital longitude. This displacement probably reflects the arc hopping between adjacent stable resonance positions. If the resonance force weakens temporarily, perhaps due to changes in Galatea's orbit, the arc material can drift forward until it reaches the next stable position where resonance recaptures it. These dynamic behaviors indicate that Neptune's ring system remains actively evolving. The rings are not ancient, stable structures left over from the planet's formation. They are young, transient features, probably only millions of years old, constantly being replenished by ongoing collisional processes while simultaneously being depleted by drag forces and orbital evolution. Webb also detected Neptune's fainter dust bands more clearly than ever before. Between the named rings lie diffuse sheets of microscopic particles. These dust bands probably originate from the named rings, as drag forces from Neptune's tenuous upper atmosphere cause particles to spiral slowly inward. As particles descend, they spread into extended sheets, filling the spaces between the main rings. The dust bands appear brightest when illuminated from behind a viewing geometry called forward scattering. Tiny particles scatter light most efficiently in the forward direction. Voyager captured Neptune's rings in forward scattered geometry, allowing detection of faint dust. Webb observed in a different geometry, seeing more reflected light from larger particles in the main rings while the dust bands appeared fainter. This difference in viewing geometry revealed that the rings contain distinct particle populations. The bright arcs in the atom's ring contain particles several centimeters to meters in size, too large to efficiently forward scatter light, but large enough to reflect infrared light well. The dust bands contain micrometer-sized grains that forward scatter visible light efficiently, but reflect infrared poorly. The particle size distributions provide clues about the collisional processes generating the rings. Webb's spectroscopic capabilities allowed analysis of ring composition. The near-infrared spectrum from 3 to 5 microns showed weak water ice absorption features. Water ice has a strong absorption band near 3 microns where OH bonds vibrate. The weak absorption in Neptune's rings indicates either that water ice is a minor component or that the ice is mixed with other materials that mask its spectral signature. The spectral data suggests the rings are dominated by carbonaceous material, perhaps similar to cometary dust. Carbon-rich particles appear dark at visible wavelengths, but can reflect infrared light moderately. This composition matches the rings' overall darkness compared to Saturn's bright ice-rich rings. Neptune's rings might contain material delivered by captured comets, or derived from carbon-rich moonlets in the outer solar system. The ring system's youth raises questions about what creates the parent bodies that collide to replenish the rings. Neptune's larger inner moons, Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus all orbit within or near the ring region. These moons, ranging from 50 to 400 kilometers in diameter, have irregular shapes indicating they are collisional fragments themselves rather than intact primordial bodies. The inner moon system appears caught in a grinding process. Orbital dynamics slowly bring moons closer together. Eventually, they collide catastrophically. The impact produces clouds of debris that spread into rings. Some fragments coalesce into new moonlets that continue orbiting until they collide with something else. The cycle repeats. Each collision feeds material into the rings, while simultaneously destroying the parent bodies that maintain them. This collisional cascade cannot continue indefinitely. Each impact grinds material into progressively smaller fragments. Eventually, the smallest dust particles spiral into Neptune's atmosphere within tens of thousands of years, removed by Poynting-Robertson drag and plasma forces. Without replenishment, the rings would disappear within 10 million years, a blink in astronomical terms. The rings' transient nature means we are observing Neptune during a special phase of its evolution. Billions of years ago, Neptune likely possessed more substantial inner moons. Collisional grinding has progressively destroyed most of that population. In the distant future, the remaining moons will collide and disappear. Neptune will become ringless, like Venus or Mars. We are witnessing a temporary state that has existed for perhaps only the past 100 million years of Neptune's 4.5 billion-year history. Webb's ring observations also revealed subtle asymmetries in the ring system's brightness. The rings appear slightly brighter on Neptune's western side compared to the eastern side. This asymmetry might result from uneven particle distributions caused by resonant interactions with Neptune's moons, or from viewing geometry effects where one side of the rings scatters light more efficiently toward Webb's position. The ring discoveries extended beyond Neptune itself. Webb captured 7 of Neptune's 14 known moons in the same field of view. Galatea, Naiad, Thalassa, Despina, Proteus, Larissa, and Triton all appeared clearly. The smaller inner moons showed as faint points of light. Triton, Neptune's largest satellite, blazed as a brilliant spike cross dominating the upper left of the frame. Triton's brightness results from its highly reflective surface. Covered in nitrogen ice, Triton reflects 70% of incoming sunlight, creating an albedo comparable to fresh snow. In contrast, Neptune appears dark at Webb's infrared wavelengths due to methane absorption. Triton consequently outshines the planet by large factors, making it the brightest object in Webb's Neptune system images. Triton's unusual retrograde orbit orbiting opposite to Neptune's rotation suggests a violent past. The moon likely formed in the Kuiper belt before Neptune gravitationally captured it during a close encounter. The capture process would have excited Triton's orbit into a highly elliptical path. Tidal forces from Neptune then circularized the orbit over millions of years, dissipating orbital energy as heat that melted Triton's interior and resurfaced its crust. The capture of Triton would have catastrophically disrupted any pre-existing inner moon system Neptune possessed. Triton's gravitational influence would have perturbed inner moon orbits, causing collisions that ground them to rubble. The current inner moon system and ring structures might be relatively recent creations formed from the debris of moons destroyed during Triton's capture and subsequent orbital evolution. Webb's ability to simultaneously capture Neptune's rings, moons, and atmospheric features in a single exposure demonstrated how ice giants serve as laboratories for studying planetary system evolution. The rings provide evidence of ongoing collisional processes. The moons reveal gravitational dynamics and tidal evolution. The atmosphere shows weather patterns and compositional structures. All these components interact, creating a complex system that cannot be understood by studying any single element in isolation. The ring revelations also highlighted how much remains unknown about ice giant systems. We have visited Neptune exactly once. Voyager 2 spent a few hours in the system during its flyby. Every subsequent observation comes from enormous distances where even Webb's remarkable capabilities can barely resolve fine details. Major questions remain unanswered. What triggers the collisions that replenish the rings? How do orbital resonances really work to stabilize the atom's arcs? What determines the particle size distributions in different rings? Why did the Liberté arc fade so dramatically? What causes the episodic brightness variations in courage? How long will the current ring system persist before collisional grinding eliminates the parent moonlet population? Answering these questions will require sustained observation campaigns tracking how the rings evolve over years and decades. Webb can provide periodic snapshots but needs complementary observations from ground-based telescopes to fill gaps. Ideally, a dedicated orbiter mission would revolutionize our understanding by studying the Neptune system continuously for multiple years, observing ring dynamics, atmospheric evolution, moon interactions, and magnetospheric processes. But no such mission currently exists, even in planning stages. The outer solar system remains largely unexplored. Neptune sits 30 times farther from the Sun than Earth. Travel time exceeds 12 years using conventional propulsion. Mission costs escalate into billions of dollars. Funding priorities favor other targets closer to home or with clearer astrobiology relevance. Webb's ring observations provided the clearest view of Neptune's ring system since Voyager 2. But they also underscored how these images are mere glimpses, brief windows into dynamic processes operating over timescales from hours to millions of years. We see snapshots, not movies. Frozen moments, not continuous evolution. The rings are revealing their secrets slowly, and Neptune guards many more mysteries still hidden in the darkness, 30 astronomical units from the Sun. Neptune's south pole refuses to follow planetary physics. While the rest of the planet cooled by 8 degrees Celsius between 2003 and 2018, the pole warmed by 11 degrees in just 2 years. This temperature inversion violates everything we understand about seasonal atmospheric behavior. James Webb captured what ground telescopes had been tracking: a continuous band of high-latitude clouds surrounding a warm vortex at Neptune's southern pole. The vortex appears as a bright hotspot in thermal infrared wavelengths, temperature 10 degrees Celsius warmer than anywhere else on the planet. This heat concentration should not exist. Neptune's south pole has been tilted toward the Sun since 2005, when southern summer began, but Neptunian summers last 40 Earth years. One complete Neptune year spans 165 Earth years. The planet receives only 1/900th the solar energy Earth receives. That feeble sunlight cannot explain the polar heating. The warm polar vortex creates an atmospheric chimney. Methane gas, frozen throughout most of Neptune's stratosphere, can escape through this hot region. Len Orton, who discovered the phenomenon, noted that temperatures are high enough for methane to leak from deep atmospheric layers into the stratosphere. This solves a long-standing mystery about why Neptune's upper atmosphere contains more methane than photochemistry and condensation should allow. But explaining the vortex's formation mechanism remains elusive. The feature resembles Saturn's polar vortices but operates under completely different conditions. Saturn's vortices are driven by moist convection from the water cloud level. Neptune's atmosphere lacks the same vigorous convective activity. Its internal heat source provides less energy. The heating mechanism must be different. Webb detected the vortex, surrounded by a spiral structure of methane ice clouds. These high-altitude clouds mark regions where atmospheric circulation lifts material above the bulk methane layer. The spiral pattern indicates cyclonic rotation. The vortex spins. How fast remains unknown. Measuring wind speeds at Neptune's pole requires tracking individual cloud features over multiple observation sessions. The rapid warming between 2018 and 2020 suggests episodic processes. The pole might experience heating events driven by atmospheric waves propagating from lower latitudes. These waves could transport energy poleward, depositing it suddenly when they break in the stratosphere. This mechanism operates on Earth during sudden stratospheric warming events when the polar vortex disrupts. Neptune's bizarre magnetic field geometry might also contribute. The field tilts 47 degrees from the rotation axis. Auroral heating occurs at mid-latitudes rather than the poles. But magnetic field lines still thread through the polar regions. Variations in magnetospheric particle populations could modulate energy deposition, creating heating variations. The South Pole mystery connects to broader questions about ice giant atmospheric dynamics. How do these planets transport heat from their interiors to space? What drives their powerful winds despite weak solar forcing? Why do atmospheric patterns vary so dramatically on decadal timescales? Neptune is revealing itself as far more dynamic than any steady-state model predicts. The pole is a window into processes we barely understand, operating according to physics that remains hidden in the darkness 30 astronomical units from the Sun. Neptune should not exist. At least not where it is, not with the mass it has, not in the time it had to form. Every simulation of planetary formation that scientists run produces the same devastating conclusion. Building an ice giant at 30 astronomical units from the Sun requires more time than the universe gave us. The protoplanetary disk, that swirling cloud of gas and dust from which all planets coalesce, dissipates within 3 to 10 million years. Neptune's core needed 10 million years minimum to accumulate enough mass to capture its hydrogen envelope. The math doesn't work. The timeline collapses into impossibility. Otto Schmidt proposed the core accretion model in 1944, Russian physicist working in Moscow during the final year of global war. He suggested that planets form from meteoric material, tiny grains colliding and sticking together through electrostatic forces and gravity. Start small. Build big, simple accumulation over cosmic time scales. By the 1970s, astronomers refined the theory. Planetary embryos grow in the protoplanetary disk. They sweep up material in their orbital zones. When a core reaches approximately 10 Earth masses, it triggers runaway gas accretion. The core's gravity becomes strong enough to capture and compress hydrogen and helium from the surrounding nebula. This envelope grows exponentially. Within a few million years, you get Jupiter. Within a few more, you get Saturn. The ice giants broke the model. At 20 to 30 astronomical units from the Sun, the disk is thin, cold. Material is spread across vast orbital distances. Collision velocities are comparable to escape velocities, meaning planetesimals bounce off each other rather than sticking together. Growth slows to a crawl. The cores of Uranus and Neptune would have required tens of millions of years to reach 10 Earth masses. But the gas disk vanished after 5 million years maximum. No gas disk means no hydrogen envelope means no ice giant. James Webb's observations of Neptune make this crisis visceral. The planet exists. It has 17 Earth masses. Its hydrogen envelope comprises roughly 15% of its total mass. Webb captured its rings, its moons, its atmospheric storms. The telescope photographed the impossible. The NICE model attempted to solve this, proposed in 2005 by a trio of papers published in Nature. Named after the city in France where astronomers Rodney Gomes, Harold Levison, Alessandro Morbidelli, and Cleomenes Tsiganis first discussed the concept. The model suggests that all 4 giant planets formed much closer to the Sun than their current positions. Jupiter at 5.45 astronomical units, Saturn at 8.18, Uranus and Neptune squeezed between Saturn and the edge of a massive planetesimal disk at 14 to 17 astronomical units. At these closer distances, disk density was higher, material was abundant, collision velocities were lower. The ice giant cores could have formed within the gas disk lifetime. Problem solved. Formation crisis averted. Except now you have 4 giant planets crammed into a space where only 2 currently exist. Something had to move them. Something violent. The planetesimal disk provided the mechanism. This massive reservoir of icy bodies extended from roughly 15 to 35 astronomical units. Trillions of comets and proto-Kuiper belt objects. Combined mass estimated at 50 Earth masses. The giant planets began migrating through this disk, scattering planetesimals through gravitational interactions. Jupiter migrated inward slightly. Its massive gravity ejected planetesimals onto hyperbolic trajectories, sending them into interstellar space or crashing into the Sun. To conserve angular momentum, Jupiter moved sunward. Only slightly. Its enormous mass meant small displacements. Saturn, Uranus, and Neptune migrated outward. When you scatter a planetesimal to a shorter period orbit, you gain orbital energy. You move away from the Sun. The ice giants plowed through the planetesimal disk like cosmic bulldozers, flinging material inward toward Jupiter or outward beyond 50 astronomical units. With each interaction, they gained energy. They drifted farther from the Sun. The migration wasn't smooth. Around 380 million years after solar system formation, Jupiter and Saturn crossed a mean motion resonance. Their orbital periods achieved an integer ratio, 2 to 1. Every time Jupiter completed 2 orbits, Saturn completed exactly 1. This resonance pumped energy into the system. Orbital eccentricities increased. The planetary orbits became elongated and chaotic. Uranus and Neptune were ejected from their original positions like bullets from a gun. Neptune careened outward, smashing through the planetesimal disk at velocities reaching several kilometers per second. The collision was catastrophic. Planetesimals scattered in all directions. Some impacted the terrestrial planets during the late heavy bombardment 3.9 billion years ago. Others were ejected from the solar system entirely. Neptune itself experienced hundreds or thousands of giant impacts during this phase. This solved the formation problem, but created new nightmares. Andre Isidoro and colleagues at the Southwest Research Institute published simulations in 2015 showing that ice giant formation through this mechanism produces the wrong results most of the time. Their models began with planetary embryos, objects with masses between 0.1 and 0.5 Earth masses, scattered throughout the region beyond Saturn. These embryos migrated inward due to interactions with the gas disk. They became trapped in mean motion resonances with Saturn, forming chains where each embryo's orbital period locked into integer ratios with its neighbors. As more embryos migrated inward, the resonant chain destabilized. The system became dynamically excited. Giant collisions occurred. The embryos smashed into each other at velocities exceeding escape velocity. These impacts were obliquity-generating events, collisions energetic enough to tilt planetary rotation axes. Uranus's 98-degree axial tilt likely resulted from one such catastrophe. Neptune's 30-degree obliquity from another. After the collisions, the surviving planets, now with masses comparable to Uranus and Neptune, continued migrating. Some simulations produced 2 ice giants in stable orbits. Some produced 3. Some produced 1 ice giant and scattered the rest into interstellar space. Only a few % of simulations successfully replicated the current solar system architecture. The statistical improbability is staggering. Our solar system required extraordinarily specific initial conditions: the right number of planetary embryos, the right distribution of masses, the right timing for Jupiter and Saturn's resonance crossing, the right amount of material in the planetesimal disk. Change any variable slightly, and you get a solar system without ice giants, or with 5 ice giants, or with ice giants in completely different orbits. James Webb's observations of exoplanetary systems confirm that our architecture is unusual. The telescope has imaged young protoplanetary disks around stars in the Orion Nebula and other star-forming regions. These disks show gaps and rings caused by forming planets. But the planet masses and orbital configurations that Webb observes don't match our solar system. Some systems have super-Earths at 0.1 astronomical units. Some have hot Jupiters at 0.05 astronomical units. Some have nothing at Neptune's distance. The diversity suggests that planetary formation follows multiple pathways: core accretion in dense inner disk regions, pebble accretion, where millimeter-sized particles drift inward and get swept up by growing cores, gravitational instability, where massive disk segments collapse directly into gas giants, planetary migration driven by disk torques or planetesimal scattering. Each mechanism operates under different conditions and produces different outcomes. Mikael Lambrechts and Anders Johansson proposed pebble accretion as the solution to ice giant formation in 2014. Their model focuses on the behavior of centimeter to meter-sized particles in the protoplanetary disk. These pebbles drift inward toward the Sun due to gas drag. A growing planetary core with even modest mass, say 0.1 Earth masses, can capture pebbles from a large cross-section of the disk. The capture is efficient. Pebbles spiral inward along gravitational trajectories, settling onto the core at rates far exceeding planetesimal accretion. A 10 Earth mass core can form within 100,000 years in a disk with sufficient pebble flux. This is 50 times faster than traditional core accretion. Fast enough to beat the gas disk dissipation timescale. Fast enough to explain Neptune. But pebble accretion has problems. It produces planets with zero obliquity. The pebbles arrive from the disk plane, settling onto the core's equator. Angular momentum conservation should leave the planet spinning upright relative to its orbit. Uranus and Neptune have significant obliquities. Something tilted them. giant impacts remain the only known mechanism. The pebble accretion models also struggle to match the heavy element enrichment that Webb observes in Neptune's atmosphere. When pebbles accrete onto a core, they bury heavy elements deep in the planet's interior. The hydrogen envelope should remain relatively pristine, dominated by solar composition gas. But Webb's near-infrared spectrograph shows enhancement of carbon, oxygen, and nitrogen in Neptune's upper atmosphere. The enrichment factors are 5 to 20 times solar values. This suggests that Neptune accreted solid material after forming its hydrogen envelope. Late accretion of comets and icy planetesimals during the NICE model migration phase. Eva Zleiman and Elizabeth Bailey from Caltech published simulations in 2023 showing that Neptune could have accreted several Earth masses of planetesimals while migrating outward. This material sublimated in the hot interior, releasing volatiles that mixed into the atmosphere. Their models tracked individual planetesimals through the migration phase. When Neptune's orbit expanded from 15 to 30 astronomical units, it swept through regions of the disk containing different compositions. Planetesimals from 14 to 18 astronomical units were relatively enriched in carbon monoxide and nitrogen due to their formation temperature. Planetesimals from 20 to 30 astronomical units were more enriched in water ice and methane. The specific region from which Neptune accreted material determined its final atmospheric composition. The simulation suggests that Uranus and Neptune accreted different amounts of material depending on their relative positions during migration. In scenarios where Uranus initially orbited farther from the Sun than Neptune, Uranus collected more planetesimals. In scenarios where Neptune started farther out, Neptune experienced higher accretion rates. This could explain why the two ice giants have similar sizes but different atmospheric compositions and thermal properties. Different accretion histories led to different evolutionary paths. But here's the nightmare that keeps planetary scientists awake. The NICE model solves ice giant formation by invoking a phase of chaos so extreme that the survival of any planets becomes statistically unlikely. The orbital instability scattered tens of Earth masses of material throughout the solar system. Jupiter and Saturn's orbits changed dramatically. The terrestrial planets experienced bombardment that delivered oceans worth of water to Earth while simultaneously threatening to sterilize the entire inner solar system. The solar system we observe is a survivor, one outcome among thousands of possible configurations that the NICE model instability could have produced. Most outcomes are catastrophic: planets ejected, orbits crossing, collision cascades that pulverize rocky worlds. We live in a solar system that threaded an impossibly narrow path through dynamical phase space. James Webb's exoplanet observations suggest that catastrophic outcomes might be common. The telescope has found young stellar systems with debris disks showing asymmetries and clumps consistent with recent giant impacts. Planets forming and destroying each other in real time. Collision cascades producing dust that glows in infrared. Planetary systems going through their own NICE model phases, most of which will not produce stable configurations. The crisis extends beyond formation. Neptune's current state challenges thermal evolution models. The planet radiates 2.6 times more energy than it receives from the Sun. Internal heat flux of approximately 67 milliwatts per square meter. This heat drives atmospheric circulation, powers storms, maintains temperature gradients that Webb observes. But where does the heat come from? Gravitational contraction provides some energy. As Neptune's interior slowly contracts under its own weight, gravitational potential energy converts to heat. But calculations show that contraction alone cannot account for the observed heat flux, not for a planet 4.5 billion years old. Neptune should have cooled more by now. Phase separation offers a potential mechanism. In Neptune's interior, pressures exceed several megabars. At these conditions, hydrogen and helium may separate into distinct phases, like oil and water. Helium raindrops could form in the metallic hydrogen region deep inside the planet, raining downward toward the core. This separation releases gravitational potential energy as the dense helium settles. The process generates heat. Saturn exhibits similar excess heat flux and likely undergoes helium rain in its interior. But Neptune's smaller mass means lower interior pressures. A phase separation might operate less efficiently or might not occur at all. The heat source remains uncertain. Some researchers propose that Neptune's interior is still differentiating. Heavy elements accreted during late bombardment are slowly settling toward the core. Water, methane, and ammonia ices crystallizing at specific pressure and temperature conditions. Each phase transition releases latent heat. The process could sustain internal heating for billions of years. Webb's observations of Neptune's thermal structure provide constraints. The stratospheric temperature anomalies require localized heating mechanisms operating on timescales of years to decades. The global cooling trend observed from 2003 to 2018 suggests long-term thermal evolution operating on different timescales. Multiple processes at multiple depths in the atmosphere and interior, all contributing to the planet's current state. The formation crisis reveals something profound about planetary systems. They are not deterministic machines grinding through predictable evolutionary stages. They are chaotic systems where small differences in initial conditions produce radically different outcomes. The planets we observe today, including Neptune with its impossible existence at 30 astronomical units, are survivor objects, products of violence and chance operating over millions of years. James Webb stares at Neptune from 1 million miles away. The telescope captures photons that traveled 4 hours from the ice giant's cloud tops. Those photons carry information about a world that survived its own formation, a planet that should not exist, a monument to chaos. Neptune's winds move at 600 meters per second, supersonic, faster than the speed of sound in Earth's atmosphere, faster than any winds measured on any planet in the solar system. These are not gentle breezes or even violent hurricanes. These are sheer forces operating at the boundary between atmosphere and vacuum. The equatorial jet on Neptune rotates retrograde, opposite to the planet's rotation. At the equator, atmospheric winds blow westward at -400 meters per second relative to the interior. This creates a velocity differential of 1,000 meters per second between equatorial and mid-latitude regions. Imagine standing at the boundary between these wind zones. The shear would tear you apart in microseconds. James Webb's MIRI instrument mapped atmospheric temperature and composition across Neptune's disk with spatial resolution never achieved before. The telescope observed discrete cloud features, tracked their motion, measured wind speeds at different latitudes and altitudes. The data revealed circulation patterns that violate every model of atmospheric dynamics. On Earth, atmospheric circulation follows predictable rules. Solar heating is strongest at the equator. Warm air rises, creating low pressure. The air flows poleward at high altitude, cools, and sinks at roughly 30 degrees latitude, creating subtropical high-pressure zones. This is Hadley circulation, named after George Hadley, who described it in 1735. Neptune receives less than 1% of the solar energy flux that Earth receives. At 30 astronomical units from the Sun, solar constant is approximately 1.5 watts per square meter. For comparison, Earth receives 1,365 watts per square meter. Neptune is functionally dark. It exists in permanent twilight where the Sun appears as a bright star, barely distinguishable from other points of light. Yet, Neptune's atmospheric circulation is more vigorous than Earth's. Wind speeds are 15 times higher. Kinetic energy per unit mass is 200 times greater. Storms systems larger than Earth spawn and dissipate on timescales of months. The Great Dark Spot observed by Voyager 2 in 1989 was a vortex the size of Earth. It vanished by the time Hubble observed Neptune in 1994. New dark spots appeared in different latitudes in subsequent years. The energy driving the circulation cannot come from the Sun. The numbers don't balance. Internal heat provides the power. Neptune radiates 67 milliwatts per square meter from its interior. This heat flux is small in absolute terms, but it's uniform across the planet's surface. Unlike solar heating, which concentrates at the equator and varies with seasons, internal heating is isotropic. Isotropic heating should produce weak circulation. No temperature gradients mean no pressure gradients mean no wind. Yet Neptune produces the solar system's fastest winds from the weakest driving force. This is the atmospheric circulation nightmare. Adam Shulman at the University of Arizona developed three-dimensional general circulation models for ice giant atmospheres, published in 2011 in Astrophysical Journal. His simulations included radiative transfer, moist convection, interior heat flux, and Coriolis forces from planetary rotation. The models reproduce some features of Neptune's circulation, including equatorial superrotation and formation of polar vortices, but they failed to match observed wind speeds. The simulated winds maxed out at 200 meters per second, half of reality. The models revealed that Neptune's circulation operates in a fundamentally different regime than terrestrial planet atmospheres. On Earth, Mars, Venus, and Titan, differential solar heating drives weather. Temperature contrasts between equator and poles, between day and night sides, create the pressure gradients that accelerate winds. These planets exist in the solar heated regime. Neptune exists in the internally heated regime. Heat emerges from the interior, rises through convection, radiates to space through the upper atmosphere. Solar heating is negligible. The planet is essentially a self-luminous body, generating its own energy and regulating its own temperature. This makes Neptune more similar to a brown dwarf star than to Earth. But brown dwarfs have different atmospheric structure. They lack solid surfaces. Their atmospheres grade continuously into compressed gas interiors, where pressures reach gigapascals. Circulation on brown dwarfs is dominated by deep, convective plumes that extend through the entire atmosphere. These plumes transport heat from the interior to the photosphere, where it radiates away. Neptune has a surface, or rather a 1-bar pressure level that we define as the surface for convenience. Below this level, atmosphere transitions to mantle. Composition changes from hydrogen-helium dominated to water-methane-ammonia dominated. This compositional boundary creates a density discontinuity that prevents deep convective plumes from penetrating upward into the atmosphere. The circulation must be driven by processes occurring within the observable atmosphere. Methane condensation at the tropopause releases latent heat. Moist convection transports this heat upward, but methane abundance is only a few percent. The latent heat release is insufficient to power 600 meter per second winds. Webb's observations of methane distribution provide clues. The telescope detected equatorial enhancement of methane extending from the tropopause down to pressures of several bars. This enhancement requires upwelling motion at the equator, transporting methane-rich air from depth. Upwelling at the equator means downwelling at mid-latitudes. This creates a meridional circulation cell with rising motion in equatorial regions and sinking motion at 30 to 40 degrees latitude. But meridional circulation alone cannot produce zonal wind speeds of 600 meters per second. You need angular momentum transport. Atmospheric waves propagating from the equatorial region toward the poles can carry angular momentum. When these waves break in mid-latitudes, they deposit momentum, accelerating zonal winds. Lee Fletcher at the University of Leicester analyzed ground-based thermal infrared observations of Neptune spanning 2 decades, published in Icarus Journal in 2014. His spectroscopic data showed that stratospheric temperatures exhibit quasi-periodic oscillations with timescales of 4 to 6 years. These oscillations correlate with changes in Neptune's brightness and cloud activity. The oscillations suggest that Neptune's atmosphere undergoes episodic instabilities. Stratospheric waves grow, propagate, and break, releasing energy that temporarily heats the upper atmosphere and disrupts established wind patterns. After wave breaking, the system relaxes back toward equilibrium, but new waves form and the cycle repeats. This process, called stratospheric sudden warming, occurs on Earth during winter when planetary waves break in the polar stratosphere. On Neptune, stratospheric wave activity appears connected to the south polar vortex that Webb observed. The vortex creates a region of anomalously warm temperatures that could anchor atmospheric wave patterns. Waves propagating outward from the vortex might amplify through baroclinic instability, extracting energy from the meridional temperature gradient. But Neptune doesn't have strong meridional temperature gradients. Voyager 2 measurements showed that equator-to-pole temperature difference is less than 3 Kelvin in the troposphere. This is remarkably small compared to Earth's 30 Kelvin gradient. Baroclinic instability requires temperature gradients to function. Neptune's atmosphere is too isothermal. Barotropic instability offers an alternative. This mechanism extracts energy from horizontal wind shear rather than temperature gradients. Neptune's equatorial superrotation creates massive shear zones between retrograde equatorial flow and prograde mid-latitude flow. Barotropic instability can amplify wave disturbances in these shear zones, converting kinetic energy from the mean flow into eddy kinetic energy. The eddies grow, propagate poleward, and transport angular momentum. Computer simulations by Yohai Kaspi at the Weizmann Institute in Israel showed that barotropic instability can produce wind speeds comparable to observations if Neptune's atmosphere has weak vertical stratification. Published in Nature in 2013, weak stratification allows horizontal modes to penetrate deep into the atmosphere, accessing large reservoirs of kinetic energy. The modes extract energy from shear zones and deposit it as zonal wind acceleration at specific latitudes. The simulations matched observed wind speeds but required fine-tuning. The stratification parameter, which describes how rapidly temperature increases with depth, needed to fall within a narrow range. Too strong stratification and the instability was suppressed. Too weak and the atmosphere became convectively unstable, producing vertical plumes instead of horizontal jets. Webb's temperature profiles constrain stratification. The telescope's measurements show that Neptune's lower stratosphere has a temperature lapse rate of approximately 1.5 Kelvin per kilometer. This is steeper than initially expected, indicating stronger stratification than Caspi's models assumed. Stronger stratification should suppress barotropic instability. Yet the winds remain supersonic. The nightmare deepens when you consider magnetic field effects. Neptune's magnetic field is tilted 47 degrees relative to its rotation axis and offset from the planet's center by 0.55 planetary radii. This creates an asymmetric magnetic environment where field lines intersect the atmosphere at different latitudes and with different intensities in the northern versus southern hemispheres. Charged particles, primarily electrons and protons from solar wind and cosmic rays, follow magnetic field lines into the atmosphere. When these particles collide with atmospheric molecules at altitudes of several hundred kilometers, they ionize nitrogen, hydrogen, and methane. Ionization produces H3+ ions that radiate infrared light at specific wavelengths. Webb detected this emission, confirming auroral activity. Auroral heating deposits energy into the upper atmosphere, at rates reaching several microwatts per square meter in localized regions. This is small compared to global heat flux but concentrated in narrow auroral ovals. The heating creates temperature anomalies and pressure perturbations that could trigger atmospheric wave activity. Rossby waves, large-scale waves that propagate westward on rotating planets, might be generated by auroral heating. These waves have horizontal scales of thousands of kilometers and periods of weeks to months. When Rossby waves interact with zonal mean flow, they can transfer momentum and energy between different latitudes. This mechanism could redistribute angular momentum and maintain equatorial superrotation. But the magnetic field variability introduces another complication. Neptune's offset dipole field rotates with the planet's 16.1-hour period. From the atmosphere's perspective, the magnetic field appears to wobble. Auroral ovals migrate in latitude and longitude over the course of a Neptune day. This time-dependent forcing should create chaotic atmospheric response rather than organized wind patterns. Unless the atmosphere has specific resonances. If atmospheric wave modes have periods that match or are integer multiples of the rotation period, resonant amplification could occur. The time-dependent magnetic forcing would preferentially excite resonant modes while non-resonant modes remain damped. This could produce organized circulation patterns from seemingly chaotic forcing. Testing these theories requires observations that Webb cannot provide. The telescope observes thermal emission at specific moments in time. It captures snapshots. Understanding atmospheric circulation requires tracking features over multiple rotation periods. Observing how storms evolve measuring how wind speeds change with season and solar activity. Neptune's seasons last 41 Earth years. Southern summer began in 2005 and will continue until 2046. Voyager 2 observed Neptune during southern spring in 1989. 35 years separate these observations. We have 2 data points across one seasonal cycle. From this, we attempt to understand circulation patterns that operate on timescales from hours to decades. The winds at 600 meters per second contain more kinetic energy than we can explain. The temperature anomalies that Webb discovered require heat sources we haven't identified. The methane distribution requires circulation cells that violate stability criteria. Every observation reveals deeper mysteries. Neptune's atmosphere is a machine we don't understand, a system generating supersonic winds from negligible energy input. A circulation pattern that shouldn't be stable. A nightmare encoded in temperature profiles and wind speeds and cloud morphologies. James Webb stares. The telescope records. The data accumulates. The nightmare persists. Neptune is common in the galaxy, statistically common. Hundreds of Neptune-sized worlds orbit other stars within 200 light-years of Earth. The Kepler Space Telescope found them by the dozens. TESS finds more every year. James Webb studies their atmospheres. We live in a universe where ice giants outnumber gas giants by factors of 10 or more. But these exoplanets are nothing like Neptune. Most orbit closer to their stars than Mercury orbits our Sun. They complete years in days rather than centuries. Their atmospheres reach temperatures exceeding 900 degrees Celsius. Stellar radiation strips away their hydrogen envelopes at rates of millions of kilograms per second. These are hot Neptunes, warm Neptunes, ultra-hot Neptunes. They occupy a region of parameter space where Neptune should not exist but does exist and challenges every formation model we have constructed. The hot Neptune desert represents one of exoplanet astronomy's deepest mysteries. When you plot discovered planets by size versus orbital distance, a gap appears. Jupiter-sized worlds exist close to their stars. Hot Jupiters with orbital periods under 10 days populate the discovery space. Earth-sized super-Earths appear at similar distances. But Neptune-sized planets at these locations are scarce, rare. The hot Neptune desert. GJ436b was the first confirmed example. Discovered in 2004 through radial velocity measurements by R. Paul Butler and colleagues at the Carnegie Institution. The planet orbits an M-dwarf star every 2.6 days at a distance of 0.029 astronomical units. 23 Earth masses, 4.1 Earth radii. Surface temperature approximately 750 Kelvin. It shouldn't exist at that location. Stellar radiation should have evaporated its hydrogen envelope within 10 million years of formation. Yet the planet persists. Hubble observations in 2015 revealed why. The planet is evaporating. David Ehrenreich and colleagues at the University of Geneva detected an enormous hydrogen cloud surrounding GJ436b. The cloud extends 50 times the planet's radius, creating a comet-like tail of escaping atmosphere that streams away from the star. Mass loss rate estimated at 100,000 kilograms per second. The planet is dying, slowly. It will survive for billions of years, but its fate is sealed. Eventually, it will shrink to a rocky core, a super-Earth, a corpse. GJ3470b is dying faster, 100 times faster. This very warm Neptune, discovered by Bjorn Benneke at the University of Montreal, loses atmosphere at 10 million kilograms per second. Its hydrogen envelope will be completely stripped within 1 billion years. Future observers will see a bare core where an ice giant once existed. James Webb's observations quantified this massacre. The telescope detected water vapor, methane, carbon dioxide, and sulfur dioxide in the atmospheres of dying Neptunes. It measured how much hydrogen remains. It calculated how quickly the envelope erodes. The data paint a picture of systematic genocide. Hot Neptunes don't survive. They transition to super-Earths, or they never existed at all. This explains the desert. Hot Neptunes are transient objects. They exist briefly during the transformation from gas giant to rocky world. Most hot Neptunes formed billions of years ago already completed this transition. We observe the stragglers, the exceptions. The planets whose formation history or orbital configuration allowed temporary survival in regions that should be lethal. But Neptune's own survival at 30 astronomical units raises disturbing questions about exoplanet demographics. If ice giants are common throughout the galaxy, why are cold Neptunes, worlds orbiting at distances comparable to our Neptune, so difficult to detect? The answer lies in observational bias. Cold planets are faint. They emit little infrared radiation. They rarely transit their stars from our viewing angle. Detection requires decades-long radial velocity monitoring or direct imaging capabilities that current telescopes barely achieve. Webb is changing this. The telescope's infrared sensitivity allows direct detection of cold giant planets around nearby stars. In 2021, observations of Vega revealed a planet candidate orbiting every 2.4 days with temperatures around 2,500 Celsius. If confirmed, this would be among the hottest known planets. But Webb also found tentative evidence of planets at larger separations. Cold worlds in Neptune-like orbits that previous surveys missed. The exoplanet WASP-107b demonstrates how Webb revolutionizes ice giant characterization. This warm Neptune, discovered by ground-based surveys in 2017, orbits a K-type star every 5.7 days. Temperature approximately 750 Kelvin. Mass 0.17 Jupiter masses. Radius 0.94 Jupiter radii. Bulk density 0.56 grams per cc. Extraordinarily low. The planet is puffy, inflated by unknown heating mechanisms operating in its interior. David Singh and colleagues published JWST transmission spectroscopy of WASP-107b in Nature in May 2024. The observations spanned 0.6 to 12 microns wavelength using HST-WFC3, JWST-NIR-CAM, and JWST-MIRI. The resulting spectrum detected water at 21 sigma confidence, methane at 5 sigma, carbon monoxide at 7 sigma, carbon dioxide at 29 sigma, sulfur dioxide at 9 sigma, ammonia at 6 sigma. 6 molecular species, detected simultaneously. In a single planet's atmosphere, this level of compositional characterization was impossible before Webb. The detections revealed that WASP-107b has extraordinarily high atmospheric metallicity, 500 to 1,000 times solar values. The atmosphere contains more heavy elements than hydrogen and helium by mass fraction. This makes WASP-107b more similar to Venus than to Neptune, despite being 30 times more massive. The methane detection was particularly significant. Methane abundance measured at 1 ppm, 3 orders of magnitude below equilibrium expectations. Chemical models predict that at WASP-107b's temperature and pressure conditions, methane should exist at parts per thousand levels. Instead, the molecule is depleted by factor of 1,000. Disequilibrium chemistry provides the explanation. The planet's interior is hot, intrinsic temperature approximately 460 Kelvin. This internal heat drives vigorous vertical mixing. Atmospheric circulation transports material from deep layers, where temperatures exceed 2,000 Kelvin, up to the observable photosphere at 750 Kelvin. At deep layer temperatures, thermochemical equilibrium favors carbon monoxide over methane. CO is the stable carbon-bearing species. Methane is unstable. When deep atmosphere material gets transported upward through convection, it carries the high CO, low CH4 composition to higher altitudes. The mixing timescales are faster than chemical relaxation timescales. Methane doesn't have time to form through kinetic reactions before the atmosphere reaches observable layers. The result is methane depletion factors of 1,000. The eddy diffusion coefficient, Ks, quantifies vertical mixing strength. For WASP-107b, retrieved values reach 10 to the 11th, or 10 to the 12th square centimeters per second at 1 bar pressure. This is 1,000 to 10,000 times higher than typical values used in atmospheric models. The planet has anomalously vigorous circulation, perhaps driven by the high intrinsic temperature creating convective instabilities that penetrate to low pressures. Neptune exhibits similar methane depletion, though less extreme. Webb's observations showed equatorial methane enhancement, suggesting upwelling motion. Ground-based spectroscopy by Lee Fletcher found methane abundance variations correlating with cloud activity. The patterns indicate vertical mixing operating on Neptune, though probably with lower K's values than WASP-107b due to Neptune's lower intrinsic temperature and different pressure conditions. The sulfur dioxide detection in WASP-107b provided another revelation. SO2 shouldn't exist in hydrogen-dominated atmospheres unless photochemistry operates. Ultraviolet radiation from the host star breaks apart water molecules and hydrogen sulfide molecules in the upper atmosphere. The liberated oxygen and sulfur atoms recombine to form SO2. The process requires intense UV flux and specific temperature conditions. WASP-107b has both. Planets similar to WASP-107b might be common. The low density and high metallicity suggest a formation pathway involving extensive planetesimal accretion during or after envelope capture. Core erosion could contribute. If the rocky/icy core partially dissolves into the surrounding hydrogen envelope, it enriches the atmosphere with heavy elements while maintaining low bulk density. Alternatively, photoevaporation could have removed most of the primordial hydrogen envelope, leaving behind a metal-enriched remnant atmosphere. Neptune's formation likely followed similar pathways. Late accretion during NICE model migration enriched its atmosphere with volatiles from scattered planetesimals. Webb's observations of Neptune's atmospheric composition could constrain how much material was accreted and from which regions of the protoplanetary disk. HAT-26b represents another compositional extreme. This Neptune-mass exoplanet discovered in 2010 has primitive atmosphere composition. Transmission spectroscopy by Hannah Wakeford and colleagues published in Science in 2017 showed that HAT-26b has near-solar metallicity. Its atmosphere resembles the composition of the protoplanetary disk from which it formed. Unlike WASP-107b's 500 times solar enrichment, HAT-26b accreted minimal heavy elements. The diversity is staggering. Two planets with comparable masses and radii have atmospheric metallicities differing by factors of 500. This implies radically different formation histories. HAT-P26b probably formed rapidly through pebble accretion before the gas disk dissipated. Its envelope captured pristine nebular gas. WASP-107b formed through slower core accretion with extensive planetesimal bombardment enriching its composition. Neptune likely falls between these extremes. Its atmospheric metallicity enhancement is estimated at 5 to 20 times solar values based on Voyager and ground-based measurements. This is higher than HAT-P26b, but lower than WASP-107b. The intermediate enrichment suggests a formation history combining gas accretion from the nebula with planetesimal accretion during migration. JWST observations published in 2025 detected sulfur dioxide in HAT-P26b's atmosphere, the first such detection in a Neptune-class planet. This demonstrates that photochemistry operates even in low metallicity atmospheres if stellar UV flux is sufficient. The SO2 abundance in HAT-P26b is lower than in WASP-107b but still detectable. This suggests that atmospheric chemistry responds to irradiation conditions more strongly than to metallicity. The hot Neptune desert's formation mechanism remains debated. Photoevaporation, where stellar radiation heats and expels atmospheric gas, explains why Neptune-sized planets at close orbital distances are rare. Planets smaller than Neptune lose their entire hydrogen envelopes and shrink to super-Earth sizes. Planets larger than Neptune have deep enough gravity wells to retain their atmospheres despite mass loss. Neptune-sized planets occupy a transitional regime where envelope retention depends sensitively on formation conditions and migration history. Alternatively, the desert might result from formation physics. Neptune mass cores at close orbital distances might migrate inward before capturing substantial gas envelopes. They arrive close to their stars as bare cores then accrete minimal atmospheres from the dissipating disk. This produces super-Earths directly, without passing through a hot Neptune phase. Webb's observations of young stellar systems might resolve this debate. By observing planets during formation, the telescope can determine whether hot Neptunes exist around young stars, then evaporate, or whether they never form at all. Preliminary results suggest both processes operate. Some young systems show evidence of massive atmospheric mass loss. Others show gaps in planet-sized distributions that resemble the hot Neptune desert even before photoevaporation has had time to act. Neptune's existence at 30 astronomical units makes it an outlier among solar system architectures. Most observed planetary systems pack their planets much closer to their stars. Multiple super-Earths orbiting within 1 astronomical unit are common. Gas giants at 5 astronomical units are common. Ice giants at 30 astronomical units are observationally rare, but theoretically expected to be numerous. The architectural diversity suggests that planetary migration is ubiquitous. Systems with hot Jupiters experienced dramatic migration. Systems with compact chains of super-Earths might have formed in situ or experienced modest migration. Systems like ours, with widely separated giant planets, probably experienced outward migration through planetesimal scattering. Neptune survived because Jupiter and Saturn exist. The gas giants' gravitational influence during the Nice model instability determined where ice giants ended up. In systems without massive gas giants, ice giant migration would follow different paths. Some might migrate inward to become hot Neptunes. Some might get ejected entirely. The final architecture depends on initial conditions we can barely constrain. Webb's exoplanet surveys provide statistical context for understanding Neptune. By observing hundreds of planetary systems at different evolutionary stages, we can map the distribution of outcomes that formation and migration processes produce. Neptune represents one specific outcome, one path through parameter space. One survivor in a galaxy where most ice giants probably exist as dead cores or escaped atmospheres or drifting interstellar nomads. The telescope's observations of WASP 166b, another hot Neptune, detected water and carbon dioxide in its atmosphere. Published results from Andrew Mayo and colleagues in 2025 showed carbon-to-oxygen ratio 0.41 plus or minus 0.08. This is close to stellar values, suggesting formation from material with roughly solar composition. The planet resides near the edge of the hot Neptune desert with equilibrium temperature 1200 Kelvin. Its survival suggests it formed recently or has unusual properties preventing rapid envelope loss. Neptune's stable position at 30 astronomical units might be unusual. Most ice giants might exist in more dynamic situations, migrating, evaporating, colliding, transitioning between different states. We observed Neptune during a temporary equilibrium that has persisted for billions of years. This equilibrium might not be common. It might be rare, a configuration that most planetary systems never achieve. The exoplanet data suggest humility. Our solar system is not a template, it's one example among millions. Neptune is not representative, it's exceptional. Understanding Neptune means understanding why it survived when most ice giants don't, why it exists where it does when most don't, why it maintains stable configurations when equilibrium is transient. James Webb continues observing. The exoplanet catalog grows. Each new hot Neptune reveals something about formation pathways and evolutionary endpoints. Each warm Neptune demonstrates chemical diversity. Each cold Neptune detection pushes observational capabilities toward the limits where other solar systems might finally resemble ours. The implications converge on a single realization. Neptune is an anomaly. Its survival is improbable. Its location is unlikely. Its stability is temporary on cosmic timescales. The planet exists because specific historical contingencies arranged themselves in exactly the right configuration to permit its existence. We study Neptune to understand ice giant physics, but we should study Neptune to understand what happens when low-probability events materialize. When statistical outliers become realized outcomes, when planets that shouldn't exist do exist anyway. "7,000 kilometers beneath Neptune's cloud tops, methane decomposes into carbon and hydrogen. The pressure at this depth reaches 400 gigapascals. Temperature climbs past 4,000 Kelvin. These conditions break chemical bonds. Carbon atoms liberate from methane molecules. They crystallize. Diamond rain falls through Neptune's mantle. This is not speculation. Lawrence Livermore National Laboratory conducted shock compression experiments demonstrating that at pressures and temperatures matching Neptune's mid-mantle conditions, methane converts to diamond. The diamonds form as microscopic crystals. They grow. They sink through the surrounding fluid like hailstones through atmosphere. Gravity pulls them downward toward regions of even higher pressure and temperature. The rain is continuous, eternal. Billions of tons of diamond precipitating through superheated fluid that our language calls ice, but behaves like molten metal. Neptune's interior structure remains largely unknown despite decades of observation. Voyager 2 flew past in 1989. The spacecraft measured gravitational field strength. It detected magnetic field orientation. It observed atmospheric composition at visible cloud layers. From these constraints, planetary scientists constructed models, educated guesses, theoretical frameworks constrained by 3 data points and enormous uncertainty ranges. The standard 3-layer model divides Neptune into core, mantle, and atmosphere. The core comprises iron, nickel, and silicates. Rocky material compressed to densities exceeding 10 grams per cc, mass approximately 1.2 Earth masses, temperature 5,400 Kelvin. Pressure 7 megabars, twice Earth's core pressure. This core condensed from the solar nebula 4.5 billion years ago during the first phases of planetary formation. Above the core extends the mantle. This layer contains 80% of Neptune's mass, thickness approximately 10,000 kilometers. Composition dominated by water, methane, and ammonia. These are the astrophysical ices. The term is misleading. At mantle temperatures exceeding 2,000 Kelvin and pressures reaching hundreds of gigapascals, these compounds exist as superionic fluids and compressed liquids, not frozen solids. Hot, dense plasma. Water at these conditions undergoes phase transitions unknown in terrestrial laboratories. Above 250 gigapascals and 2,000 Kelvin, water becomes superionic. The oxygen atoms crystallize into a fixed lattice. The hydrogen ions move freely through this lattice, like electrons through metal. The material conducts electricity. It flows like liquid. It has crystalline structure like solid. It is a new phase of matter. Marius Malo and colleagues at Lawrence Livermore compressed water samples using diamond anvil cells and laser heating, published results in Nature Physics in 2019. The experiments confirmed superionic water ice exists. The phase diagram shows stability regions matching Neptune's mantle pressure and temperature conditions. This phase of water might comprise a significant fraction of the planet's interior. The superionic water layer has profound implications for Neptune's magnetic field. Planetary dynamos require electrically conductive fluid in motion. Earth's magnetic field is generated by convection currents in the liquid iron outer core. Neptune lacks a liquid metal layer. Its hydrogen envelope doesn't reach sufficient pressure to metallize. The superionic water layer provides the conductive medium. Convection currents in this layer generate the magnetic field through dynamo action. Neptune's magnetic field has peculiar geometry, tilted 47 degrees from the rotation axis, offset from the planet center by 0.55 planetary radii. This configuration differs dramatically from Earth's dipole field, aligned with the rotation axis. The offset suggests that magnetic field generation occurs in a shell rather than at the planet's center. The superionic water layer, located at mid-mantle depths, matches this geometry. Above the superionic layer lies conventional superionic water's lower pressure counterpart, then compressed methane-ammonia mixtures. As pressure decreases toward the atmosphere, these compounds transition through multiple phases. Molecular fluids at 5 to 10 megabars. Molecular liquids at 1 to 5 megabars. Molecular gases at pressures below 1 megabar. The transitions are gradual, no sharp boundaries. Just continuous changes in density and properties as you ascend through the planet. The atmosphere comprises the outermost 5 to 10% of Neptune's mass. Hydrogen and helium dominate. Methane provides color. This layer extends perhaps 20% of the way toward the core before transitioning into the mantle. The boundary is defined more by composition than physical discontinuity. More hydrogen in atmosphere, more water in mantle. The gradient is smooth. This three-layer picture is almost certainly wrong. Burchard Militzer at UC Berkeley published computer simulations in Proceedings of the National Academy of Sciences in November 2024 that challenged the standard model. His simulations modeled 540 atoms of carbon, oxygen, nitrogen, and hydrogen at pressures 3.4 million times Earth's atmospheric pressure and temperatures of 4,750 Kelvin. These match Neptune's mantle conditions. The atoms separated into two distinct layers: water-rich upper layer, hydrocarbon-rich lower layer. Like oil and water, the layers don't mix. The phase separation occurs naturally at high pressure and temperature. The water-rich layer is less dense, it floats. The hydrocarbon layer is denser, it sinks. The separation is thermodynamically favored. Militzer's model suggests Neptune has 5 layers, not 3. The rocky core remains. Above it sits a 5,000-kilometer thick hydrocarbon layer rich in methane and its decomposition products. Above that lies a 5,000-kilometer thick water layer where supersonic water ice conducts electricity and generates magnetic fields. Above that sits the hydrogen-helium atmosphere. Between atmosphere and water layer exists a compositional gradient zone where heavy elements from the deep interior mix upward through convection. This layered structure explains Neptune's offset magnetic field better than homogeneous models. Dynamo action occurs in the water-rich shell between 7,000 and 12,000 kilometers depth. This matches the observed offset. The hydrocarbon layer below doesn't contribute to dynamo generation because it doesn't convect efficiently. The compositional boundary between layers suppresses vertical mixing. The layered model also explains why Neptune radiates more heat than Uranus, despite similar formation histories. Neptune's interior has more gravitational potential energy available for conversion to heat. The dense hydrocarbon layer sinking downward releases energy. Heavy elements like carbon settling toward the core release additional energy. These ongoing differentiation processes sustain internal heating over billion-year timescales. Uranus radiates almost no excess heat. Its intrinsic luminosity is 0.042 watts per square meter, 10 times less than Neptune's. The two planets are similar in mass, radius, and composition. Their thermal evolution should be comparable, yet one is hot and one is cold. The layered interior model provides a mechanism. Uranus experienced a giant impact that tilted its axis to 98 degrees. This collision might have disrupted interior layering, homogenizing composition, and halting ongoing differentiation. Without active differentiation, Uranus cooled rapidly and now radiates minimal heat. Neptune avoided catastrophic collision. Its obliquity is 30 degrees. Its interior retained layered structure. Differentiation continues. Heat flows upward. The planet maintains internal temperatures far exceeding what gravitational contraction alone can provide. But layered interiors create problems. Heat transport becomes inefficient. Conduction dominates over convection across compositional boundaries. Temperature gradients steepen. The interior can't cool efficiently. Thermal profiles become non-adiabatic, violating assumptions in most planetary evolution models. Daniel LeConte and Gilles Chabrier published work in astronomy and astrophysics in 2012, showing that non-adiabatic temperature profiles dramatically extend cooling timescales. Planets with composition gradients can take longer than the age of the solar system to cool, from formation temperatures to observed luminosities. Neptune might still be relaxing from initial hot conditions 4.5 billion years ago. The interior metallicity is uncertain. Gravitational measurements constrain total mass, but not composition. Models matching Neptune's J2 and J4 gravitational harmonics allow metallicities ranging from 76 to 90% heavy elements by mass. 76% means the planet is roughly 3 parts ice to 1 part hydrogen-helium. 90% means almost no hydrogen-helium in the deep interior. The 16% uncertainty range translates to enormous ambiguity in internal structure. Atmospheric composition provides constraints. Voyager measured methane abundance at approximately 2% in the upper atmosphere. Carbon to hydrogen ratio, approximately 30 times solar. Nitrogen to hydrogen ratio, approximately 3 times solar. These enrichments indicate that Neptune's atmosphere mixed with material from the icy interior. But how much mixing occurred and how deep it penetrates remains unknown. James Webb's observations of atmospheric temperature structure add new constraints. The stratospheric cooling trend from 2003 to 2018 suggests that interior heat transport varies with time. If the interior were fully convective and adiabatic, heat flow would be steady. Variable heat flux implies non-convective regions, compositional layers, or time-dependent processes operating at depth. The core mass is particularly uncertain. Models allow anywhere from 0 to 5 Earth masses of rocky material. If the core is small, Neptune formed primarily through gas and ice accretion, with minimal rock accumulation. If the core is large, planetesimal accretion dominated during formation. The NICE model migration suggests late accretion of rocky material when Neptune scattered planetesimals. This should have enlarged the core. But how much? Core erosion might occur. At temperatures exceeding 5,000 Kelvin and pressures above 10 megabars, silicate rock dissolves into surrounding icy mantle. Magnesium oxide, silicon dioxide, iron oxide. These compounds have finite solubility in hot compressed water. Over billions of years, the core might partially dissolve, distributing rocky material throughout the lower mantle. Vizan and Kessel published calculations in 2022 showing that ice can substantially mix with silicate layers under Neptune's interior conditions. The mixing creates density gradients that suppress convection and trap heat. This could explain Neptune's high luminosity and non-adiabatic temperature profiles. The interior is still chemically evolving, redistributing mass, releasing gravitational potential energy as heat. The equation of state uncertainties compound the problem. How does water behave at 400 gigapascals? How does methane-ammonia mixture compress? What are the transport properties? Thermal conductivity, viscosity, electrical conductivity at these conditions. Laboratory experiments reach a few hundred gigapascals maximum using diamond anvil cells. Neptune's interior exceeds this range. Theoretical models extrapolate. Uncertainties grow. Different research groups use different equations of state. The aqua water model by Haldeman covers 0.1 pascals to 400 terapascals and 150 to 100,000 Kelvin. The Chabrier hydrogen-helium model spans 10 to the negative 9 to 10 to the 13th gigapascals. These models are validated at lower pressures, but increasingly uncertain at Neptune conditions. Small equation of state differences propagate into large structural differences. The linear mixing approximation assumes that densities of different materials add linearly at constant pressure and temperature. This works reasonably well for hydrogen-helium mixtures. Errors are a few percent. For ice rock mixtures, the approximation is less reliable. Phase separations like those Militzer observed violate linear mixing. Real mixtures might be denser or less dense than predictions depending on chemical interactions at molecular scales. Interior models must match multiple constraints simultaneously. Total mass 17 Earth masses, radius 3.88 Earth radii, J2 gravitational harmonic 3.41 times 10 to the negative third, J4 harmonic negative 3.3 times 10 to the negative fifth, atmospheric helium to hydrogen ratio approximately 0.19, atmospheric methane abundance approximately 2%, intrinsic luminosity 0.43 watts per square meter, rotation period 16.11 hours. Each constraint eliminates regions of parameter space. Total mass and radius constrain bulk density. J2 and J4 constrain internal mass distribution. Atmospheric composition constrains heavy element enrichment, luminosity constrains internal temperature, rotation period combined with J2 gives moment of inertia. The intersection of all constraints should uniquely specify the interior. But it doesn't. Too many free parameters. Too much equation of state uncertainty. Multiple different interior structures fit available data. Neptune might have a large rocky core, or a small one, or none. The mantle might be homogeneous, or layered, or continuously stratified. The water content might be dominant. Or comparable to carbon, we don't know. Future missions could resolve these ambiguities. An atmospheric entry probe measuring composition at depth would constrain mixing ratios of water, methane, ammonia, and hydrogen sulfide. These abundances determine bulk ice-to-rock ratio. Precise gravitational field measurements would map internal mass distribution with higher resolution than Voyager achieved. Seismology could probe internal structure directly if Neptune experiences detectable oscillation modes like the Sun. Proposals exist for ice giant orbiter missions. NASA studied the Trident concept. ESA evaluated the Neptune Odyssey mission. China's space agency discussed ice giant exploration. None have been approved. Funding constraints, competing priorities. The scientific case is clear but insufficient to secure launch. Without new data, Neptune's interior remains a black box. We observe the exterior. We measure bulk properties. We construct models that reproduce observations. But the models are under-constrained. 10 different interior configurations could match all available data. The interior question matters because Neptune's formation history and evolution depend on composition and structure. Did the planet form where it is? Did it migrate? How much material did it accrete? What was the disk composition? These questions require knowing interior composition. Without that knowledge, formation theories remain speculative. The interior also affects habitability assessments for exoplanets. Most Neptune-sized exoplanets have unknown interiors. We measure mass and radius. We observe atmospheres. We estimate metallicity from transit spectroscopy. But internal structure remains unconstrained. If we can't determine Neptune's interior despite proximity and decades of observation, how can we characterize exoplanet interiors light years away? Neptune's interior is a monument to ignorance. 17 Earth masses of rock and ice and compressed fluid layers operating under physics we barely understand. The planet exists, the interior exists. We see consequences, heat flow, magnetic fields, atmospheric composition. But we cannot see inside. The diamond rain falls. The superionic water conducts. The rocky core possibly erodes. The hydrocarbon layer possibly separates. All of this happens in perpetual darkness 7,000 kilometers below cloud tops. Hidden, inaccessible, unknowable with current technology. James Webb records surface phenomena. The telescope measures what escapes. But escape is mediated by processes occurring at depths we cannot probe. The interior determines everything. We measure its shadow. The Great Dark Spot vanished between 1994 and 1995, completely, without warning. Hubble Space Telescope images from 1994 showed empty atmosphere where Voyager 2 had photographed an Earth-sized storm 5 years earlier. The spot was gone. Dark Spot 2 was gone. Neptune's southern hemisphere was clear. This should have been impossible. Jupiter's Great Red Spot has persisted for at least 350 years, maybe longer. Historical observations dating to 1665 describe a red oval at Jupiter's latitude. The storm is permanent, stable. Embedded in Jupiter's atmospheric circulation through jet stream boundaries that prevent dissipation, Neptune's dark spots last 2 to 6 years maximum. They form, they drift, they reverse direction, they shrink, they disappear. Since Voyager's flyby, Hubble has observed 6 dark spots total. Each one appeared suddenly, each one vanished completely. The planet spends roughly half its time with a visible dark spot and half without. The storms are transient phenomena operating on timescales measured in years rather than centuries. Amy Simon at NASA Goddard Space Flight Center leads the Outer Planet Atmospheres Legacy program. OPAL conducts yearly observations of outer solar system planets using Hubble. In 2015, OPAL detected a small dark spot in Neptune's southern hemisphere. The team tracked it for 3 years as it slowly dissipated. By 2018, the spot had faded below detection limits. But in September 2018, Hubble images revealed a new massive dark spot in Neptune's northern hemisphere at 23 degrees latitude. The storm measured 11,000 kilometers by 5,000 kilometers, roughly 12 degrees latitude by 27 degrees longitude. Nearly identical in size and shape to the original Great Dark Spot that Voyager observed at 22 degrees south latitude in 1989. Simon and colleagues published findings in Geophysical Research Letters in March 2019. The paper documented the first complete formation history of a Neptunian dark spot. When the team analyzed archival Hubble images from 2015 through 2017, they discovered something unexpected. Small, bright white clouds had appeared in the region where the dark spot would later form. 2 to 3 years before the dark spot became visible, cloud activity increased. The clouds were companion features, bright methane ice crystals forming at high altitude. These clouds consistently appear near dark spots, hovering around the storm edges. But finding them present years before the dark spot itself suggests that the formation process begins deep in Neptune's atmosphere, deeper than previous models predicted. The bright clouds are altitude markers. They form when upwelling motion lifts methane-rich air from lower levels to the tropopause, where temperatures are cold enough for methane to condense. The methane ice crystals are brighter than surrounding haze. They appear as white streaks in visible wavelength observations. Their presence indicates vigorous vertical motion associated with the developing vortex. If companion clouds appear 2 to 3 years before the dark spot becomes visible, the storm must originate at significant depth, possibly at 5 bars pressure levels or deeper. At these depths, atmospheric opacity is high. Dark material forming there would be invisible from above. Only as the vortex strengthens and transports dark material upward into observable layers does the storm become detectable in Hubble images. Michael Wong at UC Berkeley estimated wind speeds inside dark vortices at approximately 100 meters per second, 328 feet per second, similar to Jupiter's Great Red Spot. But these are estimates. No spacecraft has directly measured winds within a Neptunian dark spot. The measurements come from tracking cloud features around the storm edges and extrapolating inward. Dark spots are anticyclonic vortices, high-pressure systems rotating clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. This rotation direction results from Coriolis forces on a rotating planet. Anticyclonic circulation is stable at mid-latitudes where Coriolis forces are strong. But as storms drift toward the equator, Coriolis forces weaken. The vortex becomes unstable, it dissipates. This explains why dark spots have finite lifetimes. They form at mid-latitudes where atmospheric instabilities create initial perturbations. Shear between Neptune's fast equatorial winds and slower mid-latitude winds provides energy. Barotropic instability extracts kinetic energy from the mean flow and amplifies wave disturbances. The disturbances grow into coherent vortices. The vortices drift. Neptune's wind structure includes broad zonal jets extending across wide latitude bands. Unlike Jupiter's narrow jets that confine the Great Red Spot to fixed latitudes, Neptunian jets allow storms to migrate north or south. The Great Dark Spot observed by Voyager drifted across 3 degrees of latitude during the 4 months of observation. The 2018 dark spot drifted westward at 2.46 degrees per hour while also showing meridional motion. In 2020, the 2018 dark spot did something unprecedented. Hubble observations from January showed the storm moving southward toward the equator as expected. Projections suggested it would continue south, reach the equatorial region where Coriolis forces vanish, and dissipate. But August 2020 observations showed the storm had reversed direction. It was moving northward, back toward its formation latitude. Joshua Tollefson at UC Berkeley co-authored papers documenting this reversal. The storm stopped its southward motion around 4 degrees south latitude. Then it turned around. This behavior contradicted all simulations. Models predicted that vortices approaching the equator would stretch and shear apart due to differential rotation. The reversal suggested internal dynamics more complex than models captured. Simultaneously with the reversal, a smaller dark spot appeared adjacent to the main storm. This secondary feature measured approximately 3,900 miles across, smaller than the main storm's 4,600-mile diameter. It appeared on the side of the main storm facing the equator. Computer simulations had predicted that disruptions might occur at that location when vortices approach equatorial latitudes. The smaller spot vanished after several months. It might have been a fragment that broke off the main storm during the reversal process. Or it might have been an independent vortex that formed through different mechanisms and briefly coexisted with the main storm. The observations weren't frequent enough to definitively determine the relationship. Andrew Su and colleagues published statistical analysis in Astronomical Journal in 2019. Using 8,000 computer-simulated dark spots matched against 256 archival Hubble images, they calculated occurrence rates and lifetimes. New dark spots form on Neptune every 4 to 6 years on average. Each storm lasts 1 to 6 years. 2-year lifespans are most common. The detection rate depends on storm duration. Hubble would observe approximately 70% of 1-year storms and 85 to 95% of 2-year storms. This means Neptune may produce more dark spots than Hubble detects. Short-lived storms forming and dissipating between yearly opal observations would be missed. The actual formation rate might be higher than 4 to 6 years, possibly every 2 to 3 years. But Hubble's observation cadence prevents confirmation. The dark spots are vortices, but not storms in the terrestrial sense. They don't produce precipitation, they don't generate lightning. They're coherent circulation features characterized by their appearance rather than weather phenomena. The darkness results from atmospheric opacity differences. The vortex interior is cloud-free compared to surrounding regions. The exact mechanism creating the darkness remains uncertain. The 2023 theory, proposed by researchers, suggests that aerosol particles in a subhaze layer at approximately 5 bars pressure undergo darkening. Photochemical reactions, or mixing with ices like hydrogen sulfide, could darken normally bright particles. The dark material would be most visible when looking down into the atmosphere from above. Vertical mixing eventually disrupts the dark layer. Particles aggregate or sink below observable levels. The haze layer brightness gets restored as fresh particles circulate upward. The dark spot fades. This process operates on timescales matching observed dissipation rates, 1 to 3 years from peak visibility to complete disappearance. The spots are windows, apertures through which deeper atmospheric layers become visible. Analyzing their spectra reveals composition at depth. Hydrogen sulfide might be present in concentrations higher than at visible cloud tops. The particles are highly reflective despite appearing dark. They're only slightly darker than surrounding atmosphere. The contrast makes them visible in blue wavelength observations. Neptune's internal heat drives the instabilities that form dark spots. The planet radiates 2.6 times more energy than it receives from the Sun. This excess heat must escape through the atmosphere. Convection transports heat upward. But convective patterns aren't uniform. Localized regions of intense upwelling and downwelling create circulation cells that can amplify into vortices. The 47-degree magnetic field tilt might influence storm formation through auroral heating. Charged particles entering along magnetic field lines deposit energy into specific atmospheric regions. The heating creates temperature anomalies. These anomalies could seed instabilities that grow into vortices. But this connection remains speculative. No direct correlation has been established between auroral activity and dark spot locations. Comparing Neptune to Jupiter reveals fundamental differences in storm longevity. Jupiter's Great Red Spot persists because thin jet streams provide boundaries that prevent the vortex from dissipating through shear. The spot rotates within a latitude band approximately 3 degrees wide. North-south motion is restricted. The storm can't drift toward the equator where it would become unstable. Neptune's jet streams are much broader. They span 20 to 30 degrees of latitude. This gives vortices freedom to drift meridionally. Without confinement to narrow latitude bands, storms eventually reach latitudes where they become dynamically unstable. The broad jets ensure transience. Dark spots are born. They live briefly. They die. The formation precursor clouds, appearing 2 to 3 years early, suggest deep origin. If disturbances begin at 5 bars or deeper, they require years to grow and propagate upward before becoming visible. The atmosphere at those depths is dense. Pressure is 5 atmospheres. Temperature approaches 200 Kelvin. Methane exists as liquid droplets or ice crystals, depending on local conditions. A perturbation at 5 bars must overcome atmospheric stratification to propagate upward. This requires energy. Internal heat provides the energy source. Convective instabilities in the deep atmosphere create upwelling plumes that punch through stable layers. As material rises, it cools adiabatically. Methane condenses. Bright clouds form. But the main vortex circulation develops more slowly as the deep perturbation organizes into coherent rotation. By the time Hubble detects the dark spot, the vortex has fully formed. The rotation is established. Dark material has been transported to observable altitudes. The storm enters its mature phase lasting 1 to 3 years. During this phase, the vortex drifts under the influence of zonal winds while maintaining internal coherence. Dissipation occurs through multiple mechanisms. Meridional drift toward the equator weakens Coriolis forces. The vortex stretches zonally. Shear from differential rotation tears the storm apart. Alternatively, the deep atmospheric source feeding the vortex might shut down. Without continued upwelling of dark material, the visible spot fades as particles settle or disperse. The 2018 storm that reversed direction avoided equatorial dissipation. Its reversal suggests that interactions with other atmospheric features influenced its trajectory. Perhaps a developing jet stream deflected the storm northward. Perhaps a secondary circulation cell created a pressure gradient that pushed the vortex away from the equator. The data resolution doesn't allow determination. Only Hubble can observe dark spots. Ground-based telescopes lack the spatial resolution. James Webb operates primarily in infrared where methane absorption obscures atmospheric features. The spots are visible only in blue wavelengths between 400 and 500 nanometers, where contrast between dark material and bright surrounding clouds is maximized. This observational limitation means our understanding of dark spot phenomena relies on snapshots separated by months or years. Continuous monitoring would reveal evolution details. How quickly do storms intensify? How do companion clouds evolve? What triggers reversal events? These questions require sustained observation campaigns that current telescope scheduling doesn't accommodate. The dark storms are Neptune's most dramatic visible phenomena. They're larger than continents, faster than hurricanes, more energetic than terrestrial weather systems by factors of millions. Yet they exist as transient features appearing and vanishing on timescales shorter than Neptune's 41-year seasons. If human observers arrived at Neptune today and stayed for 20 years, they would witness 2 or 3 dark spots form and dissipate. They would see the planet's appearance change dramatically as storms come and go. They would realize that Neptune has no permanent features. Everything is transient. Everything flows. The dark spots prove that ice giant atmospheres are fundamentally different from gas giant atmospheres. The internal heat source, the methane chemistry, the magnetic field geometry. These factors combine to create atmospheric dynamics unlike anything observed at Jupiter or Saturn. Neptune is its own category, a regime where storms live fast and die young. James Webb cannot observe the storms, but Webb's atmospheric measurements constrain the conditions under which dark spots form. The temperature profiles, the composition gradients, the vertical mixing rates, all these parameters influence vortex dynamics. Future modeling efforts combining Webb's data with Hubble's storm observations might finally explain why Neptune produces ephemeral giants while Jupiter maintains eternal storms. The darkness swirls, the vortex rotates, the spot drifts and dissipates. Neptune's atmosphere churns in patterns we barely understand. The storms are symptoms of processes occurring at depths we cannot probe. They're surface manifestations of deep atmospheric violence. They appear, they disappear, they leave no trace except data in Hubble's archives. "36 years have passed since Voyager 2's flyby, 36 years of waiting. Of watching Neptune through ground-based telescopes and Hubble snapshots and Webb's infrared eyes. 36 years of building models from insufficient data, constructing theories from single measurements. Extrapolating planetary physics from hours of observation in 1989. No spacecraft has returned to Neptune. No orbiter. No atmospheric probe. No lander on Triton's nitrogen ice plains. The eighth planet remains the least explored major body in the solar system. A frontier visited once and abandoned. This isolation is ending. Slowly. Grudgingly. Against budget constraints and competing priorities and engineering challenges. Multiple mission concepts have been proposed, studied, rejected, proposed again with modifications. The journey back to Neptune has become a bureaucratic endurance test lasting longer than the Voyager mission itself. Trident was NASA's most recent serious attempt, a Discovery-class flyby mission targeting Neptune and Triton. Launch window October 2025, arrival 2038, 13-year cruise. The spacecraft would have carried cameras to image Triton's active plumes, magnetometers to detect subsurface ocean signatures, spectrometers to analyze atmospheric composition. One flyby, one chance to answer questions accumulating since Voyager. Louise Proctor at the Lunar and Planetary Institute served as principal investigator. The team called Triton weird, but relevantly weird. A captured Kuiper Belt object, potentially an ocean world with active cryovolcanism. Energetic ionosphere 10 times more active than any other moon. Young surface with cantaloupe terrain and walled plains formed through processes we don't understand. NASA selected 2 Venus missions instead, Da Vinci Plus and Veritas, both worthy, both addressing important questions, but both targeting a world we visited 12 times previously while Neptune remains neglected. The decision came in June 2021. Trident died. Neptune Odyssey represents the current flagship concept, led by Abigail Reimer at Johns Hopkins Applied Physics Laboratory. This would be a Cassini-scale mission. Large orbiter, atmospheric entry probe, multi-year tour of the Neptune-Triton system. Cost approximately $3.4 billion. Launch target 2033 using Space Launch System. Arrival 2049 after 16-year direct trajectory. The mission design is ambitious. The orbiter would enter retrograde orbit matching Triton's orbital plane. This allows simultaneous study of planet and moon. The atmospheric probe would separate during orbit insertion. It would descend through Neptune's atmosphere, measuring composition, temperature, and pressure profiles at depths Voyager couldn't access. Descent duration 37 minutes before being crushed by increasing pressure. Triton's active plumes provide urgency. Voyager observed nitrogen geysers erupting from the South Polar region in 1989. That South Pole remains in sunlight through 2060. After that, it enters 41 years of darkness. Neptune's 84-year seasons determine observational opportunities. The current window closes. Missing it means waiting decades. But Neptune Odyssey faces competition. The 2022 Planetary Science Decadal Survey prioritized a Uranus orbiter over Neptune missions. Uranus is equally unexplored, equally mysterious. The choice between ice giants became political, scientific, logistical. Uranus won. This doesn't eliminate Neptune Odyssey. It delays it, pushes it to subsequent decades, maybe 2040s, maybe later. The mission remains a concept, a proposal, a collection of white papers and engineering studies gathering digital dust while Neptune continues its orbit untouched by human technology. Alternative concepts exist. Triton Ocean World Surveyor, a scaled-down Neptune Odyssey without atmospheric probe. New Frontiers class instead of flagship, lower cost, reduced capability, launch 2031, arrival 2047, still under study. Nautilus, another Triton-focused concept, multi-flyby architecture, launch August 2042, orbital insertion April 2057. 45 years from now, beyond the career span of anyone currently working in the field. China's Interstellar Express includes possible Neptune encounter. Details remain vague. Launch timeline uncertain. Government approval pending. International collaboration possibilities unexplored. Every proposed mission shares common challenges: distance, travel time, energy requirements. Neptune orbits 30 astronomical units from the Sun. Light takes 4 hours to cross that distance. Radio signals take 4 hours each way. 8-hour communication lag makes real-time control impossible. The cruise duration is murderous: 12 years minimum with Jupiter gravity assist, 16 years for direct trajectory. Spacecraft systems must function reliably for over a decade before beginning science operations. Electronics must survive radiation exposure during Jupiter flyby if that route is chosen. Solar panels are useless at Neptune's distance. Radioisotope thermoelectric generators provide power. But plutonium-238 supply is limited. Missions compete for scarce fuel. Orbital insertion is the killer. Spacecraft reach Neptune at hyperbolic velocities exceeding 20 kilometers per second. Slowing down enough to be captured by Neptune's gravity requires enormous delta V. Chemical propulsion alone means carrying propellant mass exceeding spacecraft mass. Not feasible within payload constraints. Alternative strategies exist. Aerocapture uses Neptune's atmosphere as brake. The spacecraft grazes upper atmospheric layers. Friction bleeds velocity. But the maneuver is risky. No aerocapture has been attempted at an ice giant. Modeling atmospheric density profiles with Voyager-era data introduces uncertainty. Too shallow, and the spacecraft bounces back to interplanetary space. Too deep, and it burns up. Gravity assist from Triton offers another option. The Moon's gravity can bend the spacecraft trajectory, reducing velocity relative to Neptune. But Triton orbits retrograde. Matching its orbital plane requires precise approach geometry. Timing is constrained. The window is narrow. Electric propulsion provides efficient but slow velocity changes. Ion drives operate for years, consuming xenon propellant. They can achieve large cumulative delta V with reasonable propellant mass. But travel time increases. Cost increases. Complexity increases. These engineering problems are solvable. Expensive but solvable. Cassini solved them for Saturn. Juno solved them for Jupiter. We have the capability, we lack the funding, the political will. The sustained commitment required to design, build, launch, and operate a flagship mission across multiple presidential administrations and budget cycles. James Webb provides interim answers. The telescope's infrared observations constrain atmospheric models, temperature profiles, composition gradients, seasonal variations. Webb cannot resolve dark storms, cannot measure deep atmospheric winds, cannot sample interior composition. But it provides data that future missions will contextualize. Ground-based observations continue. Large telescopes with adaptive optics approach Hubble's resolution. The Very Large Telescope in Chile, Keck Observatory in Hawaii, Subaru Telescope in Japan. These facilities track Neptune's cloud activity, monitor stratospheric temperature variations, observe ring structure changes. The work is incremental, patient, accumulating decades of baseline data that eventual spacecraft observations will interpret. Exoplanet discoveries motivate Neptune exploration. Neptune-sized planets are common in the galaxy. Thousands have been detected. Their atmospheres are being characterized by Webb and future telescopes. But interpreting exoplanet data requires understanding Neptune. Our solar system's ice giants are the reference cases, the calibration standards, the examples against which all other Neptune-like worlds are compared. If we don't understand Neptune's formation, its interior structure, its atmospheric chemistry, its magnetic field generation, how can we interpret observations of hot Neptunes, warm Neptunes, cold Neptunes, orbiting distant stars? The exoplanet community needs Neptune data, urgently. The scientific return extends far beyond one planet in one solar system. The 5 primary questions that Neptune Odyssey targets span planetary science. How do ice giant interiors and atmospheres form and evolve? This is formation theory, migration history, compositional constraints, thermal evolution, questions applicable to every planetary system. What causes Neptune's strange magnetic field, and how does its magnetosphere work? This is dynamo theory, Supersonic water physics, plasma interactions, auroral processes. Questions relevant to exoplanets with offset dipole fields and unknown internal structures. Is Triton an ocean world? What causes its plumes? This is astrobiology. Habitability assessment. Cryovolcanism mechanics. Tidal heating models. Questions central to life detection in outer solar system. What is the nature of Triton's atmosphere, and how can its geophysics expand our knowledge of dwarf planets? This is comparative planetology. Kuiper belt object characterization. Captured moon evolution. Questions bridging inner and outer solar system. What are the connections between Neptune's rings, arcs, and small moons? This is celestial mechanics, resonance dynamics, collisional evolution. Questions applicable to any ringed planet. These are not Neptune-specific curiosities. These are fundamental planetary science questions, where Neptune provides the test case. The laboratory. The accessible example of processes operating throughout the universe. Yet Neptune remains unvisited, unexplored, relegated to telescopic observation and computational models. We have committed more resources to studying Mars, a planet we've landed on 8 times, than to returning to Neptune once in 36 years. The frustration in the planetary science community is palpable. Every decadal survey includes ice giant missions. Every proposal is ranked highly. Every concept study confirms scientific value, but funding never materializes. Priorities shift, budgets contract. The missions that could answer fundamental questions about planetary physics are perpetually deferred to future decades. If Neptune Odyssey launches in 2033 and arrives in 2049, current graduate students will be in their 40s when science operations begin. Current postdocs will be in their 50s. Current principal investigators will be in their 70s or retired. Planetary science careers span decades. Neptune science spans generations. The scientific return would be extraordinary. An orbiter conducting multi-year observations would revolutionize ice giant physics. Continuous monitoring of atmospheric dynamics, complete mapping of magnetic field structure, full characterization of ring system evolution, comprehensive survey of small moons, detailed investigation of Triton's ocean, plumes, and surface geology. The atmospheric probe would provide ground truth, direct measurements of composition at multiple pressure levels, temperature and density profiles constraining interior models, wind speed measurements at depth, detection of species invisible from orbit, noble gas abundances, revealing formation conditions. This is achievable, technically feasible, scientifically valuable, cost comparable to missions NASA routinely flies. The obstacles are institutional, bureaucratic, political, not scientific or engineering limitations, but priority decisions made in budget meetings and decadal survey committees. Neptune will wait. The planet doesn't care about human timelines. It will continue orbiting, generating heat, spawning dark storms, maintaining its offset magnetic field. The physics operates independently of whether spacecraft observe it. But our window is closing. Scientists who worked on Voyager 2 are retiring. Institutional knowledge is being lost. Engineering lessons from outer planet missions are fading. The gap between Voyager and eventual return mission exceeds the gap between first human flight and moon landing. We're squandering accumulated expertise, wasting momentum, letting capability atrophy. James Webb found something unexpected at Neptune: temperature anomalies, stratospheric cooling, south polar warming, methane distribution patterns, ring system details. These observations raise questions that only a dedicated mission can answer. Webb has done its part. It has observed, it has measured, it has revealed mysteries. Now the question is whether anyone will follow up, whether Neptune Odyssey or its successor will launch, whether this generation of scientists will return to the ice giant or pass the responsibility to the next generation, whether Neptune exploration becomes a 50-year gap or a century-long abandonment. The dark storms continue forming and dissipating. The methane rains as diamond through the mantle. The supersonic water conducts electricity and generates magnetism. The rings scatter sunlight. The planet exists. The science waits. James Webb looked deep into space. It found Neptune. It found impossibilities. It found a world that defies easy explanation. A planet that radiates mysteries alongside heat. An ice giant that proves the outer solar system contains physics we've barely begun to understand. The telescope did its job. Now the work belongs to mission planners, engineers, budget committees, political decision-makers. They must decide if Neptune matters, if understanding ice giant physics justifies the cost, if exploring the outer solar system is worth 16 years of cruise time and billions of dollars. The answer should be obvious, but obvious answers don't guarantee funding. Neptune waits. As it has waited for 36 years, as it will wait for decades more. Patient, mysterious, slowly revealing its secrets to whatever instruments point in its direction. But someday, eventually, a spacecraft will return. Not in 2049 maybe, not in this generation's careers, but eventually. Because the questions Neptune poses are too fundamental to ignore forever. Because ice giants are too common in the galaxy to leave our local examples unexplored. Because science advances when curiosity overcomes obstacles. Neptune will be there when we arrive.